this screencast, I will explain how to do data analysis assignment 1 using R. And this is the first data analysis assignment on my quantitative research methods course. You can see the description of the assignment here. Before I talk about the assignment, I'll talk a bit about R. So R and Stata are the two statistical software that I use. And if you think about the difference between R and Stata, one of the big differences is that in Stata, there's typically one best way or one correct way of doing things. But in R, you get lots of options. For example, you need to first pick which editor you use, because R is kind of like programming environment instead of like an integrated software. So the actual R is just a program that runs on a computer that doesn't have a user interface. I use two, and RStudio is perhaps the most common. And then I'm now switching to Positron, which is a more modern version of the same software from the same company. So the Positron is like the next generation product, and RStudio is the current product. It's more like, it's like 15 years old now. Most people use RStudio because they are familiar with it, but Positron is gaining prominence now. I'll be using mostly RStudio because that's what is available. And then at the end, I will show how Positron differs. Another thing that you need to pick when you use R is to pick which packages you use. Whereas in Stata, you will have all the commands integrated when you install the software. In R, the different data analysis and data management commands come from packages, and which packages you pick greatly affects how your R works. And I'll talk about some of those choices. All right, let's go through first the assignment, and then let's talk a bit about the differences between these two editors. And then I'll pick RStudio, and then I'll explain the decisions that you need to make when you do R. And then at the end, I'll talk about the Positron editor after I show how to do the data analysis assignment. So the assignment is here, and the instructions say that we need to do a statistical analysis, particularly regression analysis, and explain income of an occupation using other variables in the dataset. The data come from John Fox's applied regression analysis, and the description of the data is available on the course website if you want to see it as a PDF. And the idea is that we run a series of models. We try to understand what determines income, and then we document the thought process and we write a report. So the instructions tell that we run these three lines to get the data. And we are going to be using the CAR package. CAR stands for Companion for Applied Regression Analysis. And then we load the library, and then we load the data. So I'm just going to copy paste that to the editor now first. Let's talk about these editors first. So they look very similar to one another. So I'll put them side by side in one sense. So both of these editors have this panel layout. So you have this bottom panel here. there's console, and then there are tabs, and Positron has many more tabs than RStudio. The idea of console is that this is where your R works. So all the R commands go here, and all the R output appears here. So if we type 1 + 1 here, it gives us 2, and this is the exact same R that we have here. So if we type things here in Positron, then we will get the same outcome. So the R just lives in here. It's based on text. And then we have editor here. So the editor is your analysis file, and how you work with R is that you type commands either here in the console, but more often you build an analysis workflow here by typing commands into an analysis file. And then the analysis file becomes your project, which then becomes your research article. So both of these have the editor. There are some buttons here. They are a bit different. You can see here is the Anthropic logo. Here is the OpenAI logo. So this Positron editor, you can integrate various AI tools that help you analyze data. I'll demonstrate those tools at the end of the video. RStudio also has some AI assistants, but they are not nearly as developed as in Positron. And for that reason, because of the availability and power of these AI tools or AI agents, I have switched to Positron almost exclusively. I use RStudio if I need to demonstrate something to someone who is afraid of the more modern user interface of Positron. Then the similarities are here also, that there is a sidebar here. So we have things here. This shows something about our data, and this shows something about our results. In Positron, there is just a sidebar here that is empty, but once we actually load some data, then we will get information about the data here. All the plots come here. So this part here is pretty much very similar to this part here in the overall layout. So if you think about the differences that these editors have, you can see here that this is exclusive focused on R, but we can here choose that to have, for example, also Python. And then you can have multiple R sessions at the same time. So we would have Python session here, and then we can have another R session here. So we can just add here. So you could have multiple sessions of R running on parallel. And then of course, if you accidentally have another session of R, and it's going to be super confusing if you create a variable in one session and then you accidentally switch to another session and your variable of course is not there because it's defined also only in one session. So the RStudio doesn't have this for multi-session support, for example, which is one small thing less to confuse you. So if you are an absolute beginner, then I would go with RStudio because there's less stuff to be confused about. There's plenty of stuff here. I'll talk about all these features that we have here a bit later. But if you want to be a power user, then I would go straight with Positron. If you know how to use Terminal, so Terminal is this is something that I created a folder already for this project and then I deleted it because I want to show the folder creation, and then Positron is now complaining about it. If you know how to use Terminal, then you should be using Positron. So if you're like more computer savvy person, then Positron is probably a better choice. Anyone who wants to do data analysis more seriously should try out Positron and the AI features. Even though it has a learning curve, they're using generative AI to, for example, label data, do figures, troubleshoot analysis is a game changer. So I just did a project, so this is recorded in January 2026. I did a project where I fully wrote all the R code using generative AI. And I was able to, for example, troubleshoot an analysis by giving a weird result to Claude Code. And then I told Claude Code that figure out why this result is so weird. I was expecting something else. And then Claude Code went to the background, wrote some R code, ran it, analyzed the data, inspected my data, and I was doing other things. And then 5 minutes later, it explained to me that there was a problem with my data setup that caused the weird problem. And it would probably take me a few hours to figure it out myself. So it's really, really useful for troubleshooting. I also use Gemini CLI. I'll show that later in the video. To produce figures, and doing figures is a pretty tedious thing because the R code for figures tends to be fairly long because you have to specify so many different things. And I just told Gemini that I have this research question, make me figures that help me understand my data so that I can answer my research question. And then it went to the background and then it produced me like 20 figures to interpret. So it's a productivity enhancer. So I would go for try out Positron, but if you're an absolute beginner, then starting with RStudio might be better. So let's start with RStudio then. I will first make this full screen, and just a reminder, the assignment was to describe use the Prestige data. And before we go full screen and before I show the settings of RStudio, let's talk a bit about packages. So R is built on top of packages, and you install the packages either using the package manager here in RStudio or by typing install packages. The car package is something that we should use, so it gives us regression diagnostics, and then we should also think about the other things that we need to do, and we need to have a package for doing tables. We need to have a package for visualizing regression models, and we need to use a tidyverse package. I'll explain in a moment what that is, and then we need to have a package for data exploration. Let's talk about first the tabulation and visualization packages. So I'm gonna start writing the R code here. You load the libraries or the packages by using the library command. So I have these packages installed, so RStudio offers to autocomplete. I'm gonna use model summary for creating tables, and it's a good practice to document why you are loading certain packages. So I'm gonna document that this is for creating tables, and that's for visualizations. So why these two packages instead of others? We need to consider a few things. First of all, if you already know how to do something with a package, then you should use that package if that works for you. So I wouldn't switch to a new package unless there's a good reason to do so. And I used to use John Fox's effects package because the car package and the effects package are written by the same author. And it's usually, if you have packages written by the same author, then they're used very similarly. And this is something that where R and Stata differ. So in Stata, most commands follow a similar syntax, how you use the command. But in R, there is great variation between how different commands work, like how do you specify the options for different commands. And if you can have somewhat similar ways of using different packages, then it produces more readable R code, and it's also something more easier to learn for you. And why do we use the marginal effect package, and what do you generally think about when you pick a package? And I have a few things that I want from a package. One is it actively maintained? The second one is how well it is documented. The third one is that what is the feature set? And the fourth one is how does it integrate with other R packages that I might be using? So the marginal effects, if we start about the documentation, this is a really well documented package. So there is a website that contains all kinds of examples, and I can see that now there is a book about the package. So there's a lot of examples about this package, and this is great. So we want to have a well documented package, and then another thing that we want to know is whether this package is well maintained or not. So when is the most recent version released, for example? And is the maintainer still actively working on it? Like if you find a bug, how likely is it that bug is going to be fixed? Or if you encounter an error, is there some support available? What we can do is that we can Google the package. And this is the main documentation, the main website. Then there are two other important websites. One is the package homepage. So this is kind of like the official homepage. It's a bit technical information, but what you need to look at here is the date. So when is it last published? And this is published in mid-November. So the latest release is 2 months old. So that is a very new release. And it also helps to have many people here who are maintaining the package. This is pretty decent. And then we have this other URL here is where do you do bug reports? You can have it also, we can also see in the Google results. So this is updated on GitHub. And that means that this package is open source. So you can read the package source code, like you can read the source codes of all R packages. But this is also published on the GitHub, which means that anyone can read the code, edit it, and then submit patches. What we would look at here is the list of issues. And we don't care about, or the point here is not to look at if these issues if there are lots of problems already in the package, but it's that is it actively being fixed? So there's like something was a bug report that opened 4 days ago, and we can go here and we can see that the maintainer is responding. So the maintainer is actively working on making this paper better. Another thing that we can take a look at is code. There is the latest change to the code was 4 days ago. So this is being actively developed and actively fixed. So that's a good thing. So this is number one and number two. How is the documentation? It's great. We have in Marginal Effects, we have a good website. We have a book. The second one is that is the package still actively maintained, and you can check it by checking if the source code is available on GitHub and if there's actually fixes and bug issues being reported. The third is how well does it integrate, and this is something that you need to figure out from the documentation. But the two main important things that I think about integration is which different statistical models does the package support. You can read about the model support in the documentation, and I happen to know that Marginal Effects it supports a large number of models. So pretty much any model that I can think of, except for maybe latent variable structure equals models, which are really kind of tricky to visualize anyway, can be visualized with this package. So it's very hard to think about a model that I might actually use that is not supported by this package. The second one is that does it integrate with tidyverse? And I'll explain what tidyverse is in a minute. Or is it built on base R? And this Marginal Effects is based on tidyverse. So it integrates with tidyverse, and that is the final thing to consider. What does it integrate with? And the model summary is a package for building tables. It's written by, you can see here, if you compare Marginal Effects and model summary. So these websites look very similar. And this is not a surprise because it's written by the same author. So this one guy has written these two. Of course, there's like more contributors too, but he is the main author of these two great R packages. So we're going to use model summary. We're going to use Marginal Effects because they are written by the same author. They're very similar. And that means that our R code will look consistent because these packages are used in the same way, and it's also easier to learn. Both are well documented. Then I already discussed the tidyverse package, and this relates to how you use R. And there are various different ways of doing data management, and the base R data management looks like this. So if we want to, let's do a matrix. I'm just gonna do a matrix for just a small matrix of ones, and it's gonna be a 5 by 5 matrix. And if we print it out, and if we now want to pick one column of this matrix, what we need to do is do A, comma, period 1, and that will pick the first column. If we pick A, and then double brackets, then we pick the first element of the matrix. If we do A1, comma, that picks the first row. So there's a lot of learning, and it's not intuitive. What is the difference between A, comma 1, A double brackets 1, and A brackets 1, comma. What the tidyverse package does for us, that it allows us to do away with any of these, and instead we use commands like select, which selects rows, and then select variables, and a filter, which selects rows. So instead of using this archaic syntax, which also has some quirks, we are going to be using these commands to manipulate the data. So the tidyverse produces more human readable code compared to the base R. And in general, like it's a more modern set of data management, data wrangling commands. All right, so if you want to learn how to do this modern R style that I will be using, I'll talk a bit more about the differences after I've loaded the data. And then you should read this book at some point, R for Data Science. This is an open source book, and it's written by Hadley Wickham, and he's the first author. He also works for POSIT, who is the company that develops the R editors that I'll be using. So this is a great resource for learning R. You don't have to read any of these books when you listen to my screencast, but after you are done with this screencast, before you actually start to work with R on your own, I would recommend spending a few days on this book, because it explains the differences between the tidyverse and the base R, and also many other useful things to know, and it introduces you a set of packages that will get you started. It's a fairly concise book in the sense that it's fairly fast to read if you understand what you're reading, so it's not overly verbose, and I really think this is a great book. All right, so this is the website, and now we can actually go and do the data analysis assignment, and I will now make RStudio full screen. I'm just going to be focusing on RStudio for now. And the first thing that we need to do is that I'm going to start focusing now a bit more on the RStudio and the R code. We want to change some settings, and I'll show you what is available. So the first, I'm going to zoom in a bit. So Command plus allows you to change the font size, and I tend to have a font size of maybe 10 when I work on my own, but if I do a screencast, I recognize that someone might be watching this screencast on a laptop, and then it makes more sense to make the font size a bit bigger. And if we look at this user interface in more detail, there is the R file here. If we have more R files, we can do new R script. Then we have different tabs, so we can edit multiple R files at the same time. Where I would use this is, for example, if I have a project that is non-trivial in size, it's typically more than one R file. So I might have one R file that loads the data and prepares it for analysis, another R file that does the exploratory data analysis and figures and descriptive statistics, and a third R file that does my regression models. The reason why I have this in three files instead of one is that quite often I might use the same data set for different projects, and it makes sense to have like one file that prepares all the data for all the projects, and then just separate the analysis files between the projects so that there are files shared between the projects. The second reason is that it's just easier to work with when you limit your attention to only, for example, regression analysis and assume the data are loaded. All right, then we have here, that's the editor, where we can make it full screen. We can make it in a new window. Sometimes if you, for example, are running something that if you have a small screen, and it might make sense to have the editor in one desktop and then R running on another desktop so that you can switch. But we have a big monitor here, so we can have R and the editor next to each other. Then save. Source on save means that when you save, it's running. You have the search, and then here you run the file. So if we we either run the current file or we select these packages and we run them. Source is the same thing. So source means that you can run the file without printing the output. I will not talk about the exact differences between running and sourcing. We'll just be using the run button for now. Then you have your environment here. The environment means what are the data that we have. So I'm gonna load the package, and now we can see that there is A, because we created this vector, this matrix here, and it's numeric, and that shows the content. And this prestige data is now available. And if we type prestige, then it actually loads the data. And we can see here in the environment that the data contains some variables. We can expand and collapse the variable names. That's the type of the variable. So this is numeric. Numeric means decimal numbers. This is integer, means whole numbers. And then this is factor, which means that it is a categorical numeric. So we have numbers, and the numbers have labels. And categorical variables are something where they are the differences between categories are qualitative instead of quantitative. So we can say that blue color is twice as large as professional, and white color is 3 times as large as professional, for example. It doesn't make any sense. So R will, by default, just treat these as different categories, and it's going to be dummy coded in recursion analysis by default. If we want to show the data in more detail, here is the data browser. So this is useful for exploring the data. I'm going to leave it open in the tab here, so we can explore, we can sort, and we can, for example, by education, and we can filter. But important thing to understand is that if you sort the data here, this is just a viewer. It doesn't change the data in your memory. So this is just like how you view the data. And then we have here, we can load datasets here. You can save data here. I pretty much never use this. I load and save my data in code. That's your memory use. And if we want to start over, we can clear. And I'm gonna clear now because I have this matrix that I created just to show things. So I'm gonna clear, and include hidden objects means that if there's something, some data sets that, for example, a package has loaded, they will be cleared as well. So I'm gonna clear the environment, and then I will load the data again. Like so. I'm using the keyboard shortcut, so Command Enter runs the current file. I'm just so used to doing it, but you can run it from here. Then you have history tab. So history shows all the commands that I've done, and this is extends from the different R sessions. So this is when I was planning and playing around for the screencast. I'm doing data summary correlation, for example. That's from my previous time I opened R. If we want to move some of these commands to our command window, then we do to source, like so. If we want to run something, for example, if we want to run this file here, getting this matrix, we click to console, and then we click enter, and then it runs it. So you can actually rerun our previous commands. You can also rerun previous commands by using the up arrow, so you can cycle through previous commands. If we want to delete something, like we don't want to have this in the history, we delete it. And that's, I never use that because I think it's useful to document everything that you do. But there's like this feature. Then connections, this is external database connections. I've never used this, but if you are working in a corporation and you have a big database where you need to access some customer data or something, then it will be here. And then tutorial is for if you have this package, then this is like an interactive tutorial that you can run. And I've never done it before because this was introduced after I'd already known R, but it seems like a useful thing to do. Okay, so normally we have the environment tab open, so that just shows the data that we have. And then the other thing that we have here. So this part of the panel, the files is shows the files in our current working directory. So when you start a new R project, and this is now something that you should do, is you set the working directory. So we do file, and then we do, actually it's in session. So we do session and then set working directory. Quite often I have already a project open. So I open a file and then I set the working directory to the location of that file. What this does is that it tells R that whenever it saves files or tries to load something from disk, then it tries to do that from the working directory. So it's kind of like the home of your project. And we're going to do that now. And we do choose directory. And what we do here is that we do new folder. And we're going to call it Data Analysis Assignment 1. You should store the project in some place that's under your documents or somewhere else if you want to keep it. But because this is just a demo, I will just put it on my desktop and I'll delete it after I'm done. Then we're going to open it. And now we can see that our working directory, I'll run this command to set the working directory to our desktop. And the file browser also shows the data analysis assignment here. And when we have the file open, we have an R file here. It shows untitled because we haven't named it yet, and it's in red because we haven't saved it yet. We're gonna save this file now, and we're gonna save it as Data Analysis Assignment 1. And it now shows here after we refresh. Okay, so we go back and then we go here. So all the files appear here. It doesn't refresh automatically. So sometimes if you go back and forth, then you can get it to refresh. You have basic file management things here. You can delete things, rename things. I often don't use this. I use deletion because sometimes I create files. For example, I save some intermediate results which shouldn't be stored in my project. So I'll delete those as soon as possible. It's a good analysis practice that you don't save unnecessary data files. The reason for this is that whenever you save a data file, the data file never itself documents where it comes from. So for example, if we have the prestige data and we drop one observation and then we save the data, then we have a data set that lacks one observation, but the dataset doesn't document when it was dropped, by whom and why. So I strongly discourage you from saving any intermediate data files. Or sometimes you accidentally produce lots of figures, for example, and that you save, and then I would delete those. All right, so this is the file panel, and it shows you the files. Plots, if we do some graphics, I'll just do a couple of dummy graphics. The plots come here, and you can cycle between different plots using these arrows. You can zoom, and then if you want to export you can copy, or you can export as PDF or as an image. I like to use PDF figures because you can zoom into them. And we clear, and I usually clear all the figures before I get started, just to not have any previous clutter, and then I will know that any figure that I have available is from the most recent session. Then we have Packages tab, and this is all the packages that we need for the project, and I will show you next how to install a package. What we will be using also is this package called Skimmer, and this is for data exploration. If we run all these packages, we're gonna run it. we get an error message. It says that the package skimmer can be loaded because it's not available. And it's not available because I haven't installed it yet. So this is often happens that when you run R files written by somebody else, then you need to install the package. You install the package either by typing this into the command window, so we can reinstall the car package by doing that, and then it downloads the data, downloads the package and installs it. But what I tend to do is that there's user interface for installing here. So we type the name of the package, and then it asks where do we get it. So we just leave it to default. And where do we install it? We leave it to default. If you are working on a computer where you don't have administrative access, then this is set to your user directory. I never have to change this, but I could figure that if there's like some kind of weird configuration of, then you would change it. Installing dependencies is very important to have checked, because packages can build on top of another. So for example, the marginal effects requires, and the model summary requires, that you have many of the packages that Tidyverse brings in installed. So you want to pull in those dependencies, because otherwise the package will not work for you. So we're going to install Skimmer. And now if you run this and you're missing something, then you will get an error message. We can run it, and now everything runs. And if we go here, we can see which packages are loaded. So we have car loaded, car data, that is actually where the data lives. So this is the Prestige data. And the car package has car data as a dependency, so it installs that. And then a lot of this stuff is installed, like datasets is loaded by default, so that's been bundled with R when you install it. And we can search, for example, model summary. We can see that model summary is installed and it's loaded. If we want to unload a package, then we uncheck, and then we check it again. So you can see that it unloads the package and then it loads it back again. All right, then you have help, and the help file here, this is like the help browser. You'll be using this a lot with R, because the packages, one of the downsides in using R is that because it's developed by thousands of different people that contribute packages. I have programmed at least one R package, and I have contributed bug fixes and feature requests to many other packages. This means that there are different ways that packages might work, and for example, one package might call your data X, another package might call it data, another package might call it something else. So the names of the arguments to the R commands might differ. So I usually check things here. So if we want to check, for example, what does the skimmer package do? We can do it in two ways. We can do it here. So we can search skimmer. And then these vignettes, these are like more like user guides. And using skimmer sounds like something that we should read if we will start using this package a lot. And if you want to read it here, we can click here. So and this is the this just shows how to use the package with the examples. So there's we're not gonna go through this, but it's very useful to read. And you can see here that I'm recording this on January 16th, and it was updated a week ago. So this is an actively maintained package. Another way of reading this documentation is to do a question mark. So if we want to do question mark and LM is for regression analysis, then you get the help page of a specific command. And then this tells you how we use the command. I'll explain this in detail when we actually get to running the command. If you do two question marks, then it does a search of the help, and it looks for any command or any package name with LM in the title, in the name. And that gives you lots of results, because LM is a pretty common, like linear model, any extension of linear model, like GLM, it matches. So this is the help, and you can navigate this back and forth. So if we go skimmer, there are links to other to web links, and some of these links to take you to other commands, and the other commands then appear here in the help browser. Then you have a viewer, and the viewer is like a built-in web browser. When we do things, the results can appear. If the results are text, then they will appear in console. But if the results are something other than text, like if it's an HTML file, like a table, then it appears here. So this producer correlation matrix comes here. If you produce a report using RStudio, which I explained after I've done the data analysis, then the report comes here. So this like renders any output in a nice way. And then presentation, I've never used that. That's a new feature. I have no idea what it does. So this is the right-hand side. And then finally, we have the console here. So the console prints all the R commands, all the outputs. And then we have background jobs. If you are, for example, rendering a report or doing some kind of analysis that takes a long time, then you can kick it in the background. I never used this start background job explicitly, but you could do this, for example, for long data preparation tasks. Usually I have here errors. I look at this when there's a report that I'm compiling, and then if there's an error, then the message appears here. All right. I think that is covers the user interface mostly. There's some stuff here, like you can have add-ins. There's generative AI tools come here. I have tried this out, but if you want to use external tools, then the Positron editor is a lot better alternative for you than these add-ins. Then there are the menus. So there's quite a lot of things. What you need to know is the session, setting the working directory. And you can set to the source file location, or you can set choosing a directory. The global options, so this is where you have your settings. So the RStudio is a product that is developing, so the menu locations are sometimes different. I don't use the menus that much myself, because R is more about typing the commands. But setting the options, there's a ton of options. There is code. Diagnostics is something that I like to have on. So it cautions me about bad R style. It gives me error messages, like potential errors already when I type. And I have this mostly on. Not all of this is enabled by default. So then there are other things like R Markdown is for building reports. If you want to use Python, that's here. Sweave is for another kind of reporting tool. Git is for version control. If you're working with multiple different people, and if you're programming like an R package, then you would be using this quite a lot. Publishing, if you are working with something that you would publish online, like a data scientist, then this would be something that you would use. Copilot is the Microsoft Copilot. It's kind of like an AI-powered autocomplete, and you would change the settings here. But there's so much stuff here that it makes no sense to go through all this. You can go through the general and just see what's going on. All right. Now we can actually start doing the analysis, and I have the packages open here, and I will start doing the project. So what we do first is have the packages. So that's a starting point. We load the data, and the data, we could load it also from a file, but this comes from a package. So that's easy, because then we don't have to specify file locations, and you can just send this R file to anyone and they can run it. And I'm gonna run it, and we're gonna source. So source runs the full package, and then I'll just switch that on. And now we need to think about the different ways of using R. And if we want to view what is in the data, which is the first thing that we do. We need to export the data. There were a few ways, so we can eyeball it here, and we can see the values. So this shows us a few first values of each of these variables, or we can eyeball it here, or if we type the name of the data here, then it prints the data to the console. And then if we want to have just view the data, like not have this use printout, we can do head data. That shows us the first observations. Now, if we want to select a variable from this data, we have a few options. Let's say that we want to select education. So there are now 7 different ways to select the education variable, and I'll explain now why I want to bring up these 7 different ways. If you think about how the data are structured in R's memory, there are what we call data types. And the data type, if we look at the prestige, we can do class prestige. It is data frame. And so the data frame is like an Excel sheet. It's like a data set with rows and columns. Data frame allows you to have columns to have different data types. So you can have a string, which is text in one column, and then numbers in another column. And technically, it means that the data frame is actually something what we call a list. So a list is just a collection, an ordered collection of elements. So the data frame is actually a list of vectors, which is equals to numbers or texts. So it's a list of vectors. And this, if we access a member of a list, we access it like that. So we can access the education. So this will give us the education value. So it is the content of the first variable, a first element of a list, which is the education variable here. We can also access data frame as if it was a matrix. So matrix is this 2x2 arrangement of data. And this gives us I should do it correctly. So this gives us the first column of the data. And it does the same thing. If we do it like this would give us the first row of the data. So it's indexed, and it's if we want to have the first value, then we would do for example 1 by 1, which gives us the first value. If we do head prestige, we can see that that's the first value in the data. So you can access these based on either as if it was a list, or you can access it as if it was a matrix. So and this prestige 1, this gives us the first element of a list. So that gives us the prestige. But then again, if prestige, if it was a different kind of data, like another way of storing data is a matrix, and matrix is kind of like a data set, but all the variables have to be of the same type. So you might have like all numeric, then it might be a matrix. Then this would give you, if this was a matrix, it would give you the first number in that matrix instead of the first column of the data. So there's one big confusion about this way of doing R is that if you have a different data type, if it's a data frame or a matrix, then this will produce you a different result. This gives you the first element. So this gives you a subset, and this gives you a first element. They produce the same thing in this case, but that's not always the case. You can do indexing based on row or column numbers. So we can see here that this data set has column numbers. So that's the names of the variables. And it also has these row names. And that gives it the column names, and we can do row names and that gives you the row names. So we can index based on these row and column names. So prestige education, yeah, we need to, it's not row education, but it's column education. You can see that it's very easy to, even if you're an experienced R user, when you type and talk at the same time, to have the comma in an incorrect place. So that's the right way of checking the education. Or we can access them as if they were list elements. That gives you the same thing. So this is super confusing for a beginner, and all this referring to variables based on their index is also really error prone. And with variables, it's not as bad practice as if we were selecting rows, because variable order rarely changes. But when you work with data, it's quite often that you sort your data. And if you sort your data, then of course a row index would then refer to a different observation. So to not have to worry about any of this stuff, we're going to be using the tidyverse function. So the tidyverse is a collection of more modern way of using R. And instead of selecting things with square brackets, we're going to use the select function. So the select function is from the package, and how it works if we do select is that we give where do we select from and what do we select. And you can also see that here we had to specify this education in quotes because it's a string, and then this select package is a nice package because it doesn't require the quotes, it works without. So we're going to be using this style of R throughout the project. We will not do any of that stuff. Another way that you often see in let's take a look at the documentation of the select, and it comes from dplyr package, which contains various data management functions, and it's included in the tidyverse package. So tidyverse is kind of like a package library that brings you all kinds of goodies. And so there's lots of explanations of how this selection works. We're just going to use the basic stuff, so we don't need to read this. This documentation here is more for those who already know how to use this command. And it's kind of like a reference. It's not a user guide in the sense that it's not a tutorial. If you want to read a tutorial about how to use this select function and other data management functions, then you should read the R for Data Science book instead of reading the documentation. So the documentation is not really a learning resource in most of the time. It's more like a resource for those who already know what they're doing. All right. This is another way of doing functions in the tidyverse style, and this is called a pipe. And the idea is that you take the prestige, and then you use a function to apply to the prestige data. And if we look at the select function, it takes data as the first argument. And this is a way of chaining together commands. So if you want to see, for example, the value of education for the top observations, we could pipe and then we do head. And that would give us the top values of observations. So this is for chaining data processing commands. We will be mostly using this style because the data management that we do in this project is fairly simple, but you will see this style quite a lot in real projects, like bigger projects. When you have to do, for example, group data and then calculate means based on groups, it makes a lot of sense to chain the grouping and then the calculating means by group commands into one sequence like that. All right, so this is the how we select observations, and let's now get started with actual analysis. And we have loaded the data. So the first thing that we do, with the analysis is that we need to understand what these data are. And we can of course eyeball, but eyeballing the data is not something that is the most productive way of doing data exploration. Instead, we're going to use the skim function. So the skim, and then prestige. Or we could do it with pipe, but that would be a fairly unusual way of doing it. So we just skim the prestige data, and this gives us a descriptive statistic. So we need to first understand what do we have, what are the data types. So we have 102 observations. So this is 102 occupations. We have 6 variables. One is factor. Factor is categorical, and then 5 numeric. We have information about each variable, and because categorical variables and numeric variables are typically analyzed and summarized differently, we have 2 different sections here. And the type is the occupation type. We have 4 4 units of missing data, so we can take a look at what those are in a moment. And it's not ordered, so we could have ordered categories. For example, if you think about the rank, like being first in a running competition, being second, and being third, this is an order, but it doesn't mean that the difference between the first and second and third is the same. So ordered means that there is data that has an order, but the differences between the different categories are not equal or are not known. So for example, if you think about distances, then 2 meters is twice as much as 1 meter. 3 meters is 3 times as much as 1 meter. But we can't say that being a third is twice as much as being first, for example. So this ordered categorical variables, we don't use those in this assignment. But if you would use them, then this would be true. We have unique values, and then we have frequencies. We can see the frequencies that we have: a blue collar professionals 44, professional 31, and then white collar 23. So this is from this we would infer that these are approximately kind of like in the same ballpark. So it's not that one of these professional types is very rare compared to others. There's of course differences, but the differences are in the same ballpark. It's not like one would be 10 times as frequent as another. If we want to understand what are these missing values, we could do a filter. So filter selects rows from your data. Select selects columns, filter selects rows. So we can filter prestige. I just use Stata, and Stata contains uses the missing function for missing data. If we want to check which observations are missing, then you use isNA. So NA is the missing value in Stata, and we can see that these 4 observations have missing values for type, and athletes, professional athletes, newsboys, babysitters, and farmers are not covered by this occupational classification. This is actually a useful command, so we could have it here. So sometimes when you explore data, you would just type commands here, and when you find something that is useful for your report, like you need to make note of it for future, or you need to report it in your article, then you put it into the data analysis file. And it's a good practice to save this occasionally. So I just press Command S as a matter of Control S in Windows as a matter of routine. Then we can look at the other variables. We would interpret this, and let's focus on education first. Education is years of education. These data come from Canadian census from 1970s. The education levels at that point were lower than today. So the average is 10 years. Standard deviation is 2.7. And then this gives you the percentiles. So P0 is the minimum. The minimum is 6.3 years. P100 is the maximum. So this is 16. So these data are from the histogram that they are close to uniformly distributed. There's this small bump here, and you can see that the median and the mean are the same, which kind of indicates that there's some degree of symmetry in the data. The standard deviation then tells us that most of the observations are plus or minus one standard deviation of the mean. So most means that if it's normally distributed, then it's around 2/3. So this would mean that minus 10.7 minus 2.7, so that's 8. So 1/3 would be below 8. And then when you add this together, that becomes 13.4. So about 1/3 is above 13.4. Then we have income. The income here is skewed, and skewed means that there's a lot less data on one end of the variable, and we can see it from this histogram. And this histogram shows you that bulk of the observations is here, and then there's this long tail here. The maximum is 25,000, the minimum is 6,000. So the maximum is 4 times as much as the minimum. The minimum is 600, and then the maximum is like quite a few times the minimum. The mean is 6,000. The maximum is 4 times the mean, so there's some income inequality. The share of women is highly skewed. There are some observations or a lot of occupations with no women. And then other than that, they seem to be the distribution seems to be rather flat. 25% is the average, and that might indicate that women work less in this data, or it might indicate that the women are concentrated in some professions, and then there are many professions with no women. The prestige score, we can see that the range is from 14 to 87. And that's the observed range. I think conceptually, this variable is defined between 0 and 100. So 100 is the theoretical maximum, 0 is the theoretical minimum. But in this case, empirically, the range is about 70 units. So it's from 14 to 87. And we need to keep these ranges of this data in our mind when we interpret the data. Then this census code is something, it's just a numerical code. It doesn't give us any information. So we can drop it, but it doesn't really, if we want to drop it, then we would select it out, but it doesn't really hurt to have it there. We can drop it in the final tables that we do, but just to have it here as an identifier, it doesn't hurt. So we will keep it in the data. The next thing that we do is that we look at these variables one variable at a time. How we do this univariate analysis is that we have already inspected the means and standard deviations, but we look at the distributions. And how we do that, I like to use a command called stem. So this produces stem and leaf plot. And we will first do education. So we do prestige, and then we do education. And then we run it. You can either just press Command Enter or Control Enter in Windows to run the current line, or you could go from here. What this shows us is kind of like a distribution of the data, and we can have the density plot or the histogram. Let's do histogram. So if you think about this histogram, so everyone knows what a histogram is. So this shows the relative frequency, or the actual frequency, because this is categorical, actual frequency of observations in these bins, and this is like binned based on year. So this is from 6 to 7, 7 to 8, and from 15 to 16, roughly. This is the same thing, but it's sideways and in numerical form. So it's kind of like a histogram of the data, and how you read this is that it tells you where's the decimal point. So this means 6.4. There's one observation. Then we have here, you can see that this kind of like shows you the height of the bar. We have here 7 observations, 6 observations. So this means that we have here 6 observations, 6.6, 6.7, 6.7, 6.7, 6.8, and 6.9. And this is 3 observations, 7.1, 7.4. So this stem and leaf plot not only tells you the shape of the distribution, but it tells you the values in 2 digits in 1 digit precision here. So we can see here that this is roughly uniform in the sense that there's a little bit of more observations in the middle. You can see here a little bit more observations in the middle than in the ends, but there's like no like normal distribution shape or no like skewed shape that we have in other variables. When you analyze the data, you would do this for all the observations, and before we start doing the other observations is which one of these should you prefer. So you can have this histogram, or you can have this density plot, which is kind of like a continuous way of doing a histogram. So this shows the relative frequency of each observation. The area under the curve is 1. So this doesn't tell you the absolute number, but just the relative frequency. It's a matter of preference. And I like to have this density plot. Just like for some reason I prefer it over the histogram. Other people like histogram because it's maybe because these are the absolute frequencies instead of the relative frequencies like the density plot. Still others like the stem and leaf plot. I tend to favor, when I do data analysis, the stem and leaf plot. The reason for that is that if I happen to work on laptop, for example, then I would work with this minimized, and I just see the data here. And this is also, I have this minimized also if I have my screen oriented in portrait mode, and this allows me to focus more. So I don't have any of this stuff shown. So the less stuff I have shown, the more I can focus on the things that I have here shown. And the second reason why I prefer this one is that then I have one place to look at. So there's one sequence of results that I look at, and I can also see the command here, whereas these plots are kind of like on the side. The third is that in some cases, this is a bit faster to calculate. It doesn't make a huge difference, but this is like my preference. Some other people prefer the graph. So whatever works for you, pick one. You don't have to do all of these for every variable. But it's useful to document the distributions of the variables using one of these options. And I'm gonna use this stem and histogram. So income, we can see that it's skewed. So how do you interpret this plot? What do these numbers mean in absolute terms? We need to first understand that the decimal point is 3 digits to the right. So that means that this is actually 2000. So 3 digits more. It's 2000, 4000, 24,000. Except that now we see a bit of a problem here because the stem and leaf plot is also binning. So this is everything below 2000. So this is actually 900, and this is 1000, 1700, 1900. How do we know that it's 1000? These are 1000, and these are 0,000s. We know it because the numbering restarts here. So this is like in order. But here we wouldn't have any way of knowing if this is 18,300 or 19,300. It's like the same binning problem that we have here. We can adjust the binning in both of these commands, and when you want to adjust the default settings, the easiest way, or the way to do it, is that you look at the documentation. So we do question mark and then name of the comment, the command. There is lots of stuff here, and we should look at breakpoints. So this sounds like something that we should have. There's different ways to define the breaks, and we can either define them manually. If you go and we do plots. So let's see that we have now 1, 2, 3, 4, 5, 6. If we do histogram, let's do histogram, and then we can do breaks. Let's do 12, and then we run it. That gives us something. It gives 12 bars, but the problem now here is that it still doesn't break this into 5 bars by 1000s. What we can do instead is that we can do a sequence. So there are 2 ways of doing a sequence, or many different ways, but two that I like to use. So we could do from 0 to 25. So that would be 0 to 25,000, and then we multiply that by 1000. So that would give us a sequence. So we could use that in the breaks, and we need to make sure that it covers the data. So there's 25,000 something is the top value. So now this is, each of these bars is 1000. So this is more useful for us to do. Another way is to use the works is to use the command sequence. So sequence command gives us from, to, and by. So we would do sequence 0, 25,000, and then 1000. That gives us a sequence. Which one of these is better? If you are very good at R, you would know what this first line means, this one. But this is more readable. We could make it even more readable by saying from, to, and then by. So we're naming these arguments. You can see from, to, and by. Naming is not needed because R will infer the position. So it knows that if we don't name, the first one is from, the second one is to, and the third one is by. But this is more readable, like sequence from 0 to 25,000 by 1000. So that would be a way of doing the histogram. If we want to do the same for the stem and leaf plots, we can do check the documentation. And this documentation scales, controls the plot length. We would adjust the scale, and it's not documented what it does, so we can just try different values. So if stem is not enough, it doesn't do what we want to do, let's do scale equals 2. So 1 is the default value, and then scale, and that gives us, so this is what we wanted to have. So we could do income and then scale equals 2. So that gives us a plot that allows us to say that these are the observations under 1000. This is from 1000 to 200,000. This is from 2000 to 3000. This is from 3000 to 4000, and so on. So this is how you do the distributions, and then we would do the rest of the data. So I would do stem, and then we do prestige. The easiest way to repeat the command is just to copy paste it, and then change. We do it for women. We would do it for prestige. The type variable is a factor. We don't do the stem and leaf plot. It doesn't make any sense to inspect the distribution of factor. So we would inspect, and we would see that the women is skewed. So there are lots of occupations with very little women, below 10%. And then other than that, it seems to be roughly uniform, so that there's no big pattern here. The prestige looks like somewhat normal. So most occupations are here. It's a bit skewed, so that there are less high prestige occupations than there are these with a bit lower prestige, but it's nothing substantial. So this looks okay. All right, next. This is the univariate analysis. One more thing about the univariate analysis is that we would use table and prestige, and then we can do type. So inspect the relative frequencies of these types. We already had that in the scheme. But if you think about a data analysis, explore data analysis pipeline or workflow, there is typically like one eyeballing stage where you just eyeball the data. This is what we would do with Skim. And then we would have a more detailed univariate analysis. So you would eyeball and then you would again look at every variable individually that you're going to be using. Next that we do is pairwise or multivariate. We need to understand correlations and then we need to describe the data. There are a couple of ways of doing correlations, and the base R provides you core, so we can do just core prestige. And now we get an error. And the error that we get tells us that we have a variable that is not numeric. And the non-numeric variable here is the occupation type. So how do we deal with this problem? We can do we can see where it happens here in traceback. So it's core prestige that gives us the error. This is useful if you have bigger projects and you run into an error deep into an R file, then you know where the error happens. But here we know that it happens in the correlation. So we need to select out the type variable. And how we select out, as we do select, and then prestige, and then we will do minus type, and that selects out the type. So minus selects out. If another way would be to select the variables from education to reduction in census, so to prestige. So that works. And then this works. I would prefer the second one because we want to tell what we are focused on instead of saying what we are not focused on. So the select allows you to separate selection criteria with a comma, and then it tries to figure out what you mean by that. Okay, but this is not like very nicely printed correlation matrix, because normally we would like to have significance tests, for example, and we would like to have maybe lower diagonal, maybe have less digits, because this is symmetric. Then it doesn't make any sense to print out both. So what we would do is that we can use the model summary package. The model summary package contains lots of useful things for tabulating data, and because the correlation table is a table, then the model summary package will actually have a function for doing the correlation table. So we can do model summary to show the package documentation, and then we scroll down here, and this is the overall information. I know the function that I'm looking for, so we click on index, that shows the list of all functions, and I want to see data summary correlation. So the data summary correlation, it gets the data. So let's do data summary correlation, and then we have select prestige, education prestige, and we can see what it gives us. And now we have it prints us the correlation table here. This is a lot nicer to interpret, because this is something that you would have in a research article. If you want to have it in the console, then you add the output. So the output here is it defaultly does HTML, so that's like a website and it opens the viewer. We can do output equals markdown, and that prints it into the console. So this is like a matter of preference. I prefer to have things in the console. Other people prefer to have difference in the viewer. Then if we want to have the significant stars, there's an option stars, and when we do this stars equals true is the default, so that gives you the stars. If you want to have non-standard star levels, you can specify them here as well. Okay, and now we run into a problem that we have to have an object produced by correlation package. Now the documentation here shows us that if we want to have stars, then we need to have the correlation package. And what we would do is, now that we add that package into our workflow, and we would load the correlation. So this is how you add the packages while you edit the project, and we will run that, and I have it installed. If I didn't have it installed, then I would do install packages here and then correlation and install it from here. But I have it installed because I've used it in the past. And then we can take a look at the documentation again. So what we would do is that we have data summary, correlation, and then we would do correlation select. So that gives us the significant stars. So let's take a look at what this does in more detail. So this is actually a sequence of commands. So we have this correlation here, and we can do correlation analysis. And now we are storing the results of this command. So we are creating a new object. This far we just have the prestige data. And we can also do this correlation analysis separately. We will do this a lot when we start running regressions. So we will not just like run a regression and print it at the same time, but we typically run regression, store the results, and then we do stuff with the store results. So we do the correlation analysis, and then we print, we do it first, and the correlation analysis, if we want to view the results, we can do print it here, and this gives us correlations, but it's not in matrix form. So yeah, this is very detailed correlation analysis. I like the summary more than this detailed analysis. We can also do summary. So summary is another way of printing our results, and it prints typically a bit more readable version of the correlation. So this is a correlation, but it looks pretty weird because it's not like we would normally view a correlation. There are all these variables present, but it's like usually you would have the lower diagonal shown, and this is like some weird arrangement. So these are not even in the same order in the columns here. So this is not very intuitive way of looking at correlations. So the data summary gives us a more useful, more user-friendly way of reading what the correlation matrix is about. Because we are not doing anything else for this correlation, we'll just change the commands. So, and it's a good idea to not make to keep your line length shorter than this 80 character mark here. So you might not have this visible, but don't make your lines too long, because then you have to scroll left and right on a small screen. So we do a line break. R has support for multi-line commands, so it will stop interpreting the command when the command is complete. It will not stop here. So this will be a nice way of printing the significant stars, and we have the markdown to print it on the console. If we want to print it in the viewer, we would do this instead. So then this is like we could just basically screenshot this and put this into a paper. There are better ways of getting this into a paper. So you can, the data summary correlation also exports Word documents. So if you want to get this into a paper, then you export as Word and then you copy paste from the Word. But if you just want to do a quick and dirty analysis, you screenshot it, and then you send the screenshot to a co-author, you screenshot the copy to a paper. All right, I'm just gonna leave it there in the console. All right, so this is the correlations, and the next thing that we want to do is to do the same visually. So correlation tells us the linear associations between the data, but it doesn't tell us if the associations are, if they are actually linear. So if you have a variable that is associated in an exponential way, they are still correlated, but the correlation doesn't tell us that the relationship is exponential in nature, and it also doesn't tell us if there are any outliers. So we don't know how systematic the difference is. To do that, we would do graphical diagnostics or graphical analysis of the relationships, and we can do a scatter plot matrix. There are many different ways of doing scatter plot matrix. The pairs is something that we can do, and that's a built-in command. So we would do pairs, and at this point, because I know that I will only be using these variables, I don't want to type the select at every stage of the analysis. I will take a subset of the data, so subset of the variables. So now if I use the prestige subset, which has 4 variables, then I don't have to type this select in all my commands. This simplifies the code. The downside is that now I will need to remember what is the difference between prestige and prestige subset. So there is like a balance that you shouldn't do a new data for every possible subset that you might use, but you need to be a bit more selective. So this is the, we're just gonna change the commands so that we're gonna be using the prestige subset. All right, so how do we then do correlation matrix? We can use pairs, that's a built-in. That's a built-in. So this is from the base R, and it shows us something, but there are other ways of doing the same plot that gives us even more data, even more results, or more information. We can do scatter plot matrix from the car package, and we do prestige subset. So that shows us more information because it shows us the distributions, and it shows us fits, and we can have both here, and then it's a matter of preference which one you prefer. I prefer this one, and then there's like pretty much every regression analysis toolkit package that you can imagine in R contains this plot, a different version of this plot. So this is I'm gonna copy this to our R file. What I haven't mentioned yet, which should be obvious by now, that this hash marks a comment. It's colored green by the RStudio editor. These warnings are here because R doesn't recognize that we have, it doesn't really recognize that the tidyverse packages actually see this type and census. So this not in global scope means that when you have a variable, like this is the variables that we have. We have correlation analysis table, which we can actually, we should actually drop that because we don't need that. And then we have prestige and prestige subset. So this warning is just that there is no type or census variable. And this is because they exist inside the prestige. And then the select sees inside prestige, but the data editor is not aware of that. So when you have these warnings, you can check what they mean, but then some of these warnings are harmless. So this is a pretty harmless warning. All right, we're gonna run then start inspecting what this means. And when I inspect results, I typically like to make this a bit bigger, the plot. And so these just show the density plots that we already saw. And this is called a RUG plot, so it shows you where the actual observations are. and it's useful to see how many outliers there are. So most of the data on income are here, and this is the range, so they're clustered around 5,000, and then we have one at 20,000 and two at 25,000. But what we would really be looking at here is the shape of the distribution, or the shape of the bivariate distribution. So how do two variables relate to each other? And this is symmetric in the sense that this is the same data, it's just flipped. So this observation here is the same as this observation here, and this observation here is the same as this observation here. It takes a bit of training to see that they're the same. The plot, the lines that we have here is that this is the linear fit. So we can see that the line doesn't really explain the relationship between education and income that well, because all these mid-income occupations are above the regression line of education, and then these high-income occupations are below the regression line of education. It's easier perhaps to see it from, or more intuitive to see it from here, where income is like the dependent variable in the regression. So we can see that the regression line fitted to the data goes here. There's more observations below the regression line here, and then more observations here. And this is some kind of non-parametric line. So it's probably a lowest fit, and it shows us what is like the best fitting line or best fitting curve if we don't constrain ourselves to be linear. And here we can see that it's clearly a non-linear relationship, and here it's not as easy to see it here, but it's clearly education and income is non-linear. Income is the main dependent variable, so we should be concerned about the income's relationship with other variables. And so we would be looking at this line, which has income as the dependent variable on the y-axis. So the next thing we can see that with prestige, it tends to be associated very strongly. So very strongly means that these points are tightly clustered around the regression line, and then it breaks apart in the high income occupations. So it seems that most of the high income occupations earn more than what is linearly predicted by prestige alone. So you can see here, this is the name of the axis. So this is the name of the x-axis, and it's the name of the y-axis for these. So this is the income is the y-axis for these plots, and it's the x-axis for these plots. We can also see that there are only few these high income occupations that are not explained well by the line. The share of women has an interesting relationship, so it varies between 0 and 100 to income, in that when there is a large share of women in the occupation, then the occupation is going to be low income. If there are not many women in the occupation, then there's a lot of variation in income. So having a large share of women in an occupation guarantees that it is a low income occupation. But if it's a low share of women occupation, then it can be a low income occupation, or it can be a high income occupation. And this is called heteroskedasticity. So it means that the variance of the data changes along the regression line. So the variance is not constant. If the variance was constant, then this band here would be equally spread out regardless of which part of the regression line we look at. So then we look at the other relationships. There is no clear pattern between education and women. The fit here says that yes, there is, but there's always like if you fit a curve to some data that's small, it's hardly ever exactly linear. So I would say that there's no pattern. Then the share of women and prestige. There's a slight pattern in the regression line. It goes down a bit, but if you just eyeball this figure, this could go down just because there's not that many observations here. So I wouldn't make any definite conclusions about there being any relationship either. Then the final thing, so we looked at income. we look at women, the final thing that we need to look at the education and prestige. And the education and prestige relationship is strong. It looks to be fairly linear, maybe some small degree of non-linearity. You can see the dashed lines, but I would still say that the just looking at this figure now, I would probably go with the linear relationship that is homoscedastic, because the observations tend to be approximately equally spread out around the regression line. You can view the same thing. This is the base pairs, so it's the same data, but it doesn't have these graphics overlaid that show the fits. So this is exactly the same plot, except that this adds these nice lines and nice areas that you can use to help to interpret the data. So I prefer the scatter plot matrix from R instead of the base pairs. Now we're done with the data exploration, and the next thing that we do is regression analysis. But before we start doing regressions, we're going to do a bit of housekeeping with the R file. And one useful thing to have in the R file is to have headings. And the headings allow you to navigate the file. So here you can see that there's this navigator, but we don't have any functions and we don't have any headings. And it's not very useful because it doesn't show us anything. So what we're going to do here first is that we will add a special kind of comment. So this comment is going to show in the navigator, and we'll write the important thing is this 4 equal marks. So that defines a heading, and we will define data exploration, and then we will define univariate analysis. We will define bivariate analysis, and then we will do some regression models. And I know that I would be doing 3 or 4 regressions, so let's just do headings for these already. So now we have the file structure here, and we can see from here we can navigate the file easily to go to different parts. And if you want to have like different levels of headings, then you can do it by adding more hashes here. So it's always 4 equals marks, and then the hashes in the beginning of the comment determine the level. We can also do the same with having 4 hashes at the end, and that will also show here as a heading. I prefer the equals marks because I think that's the original style. All right, now that we have the headings, we are going to do the first regression. And the regression that we're going to do is we do LM, which is the command for regression analysis. And the documentation here says there's a formula. So the formula is something that typically has a left-hand side and a right-hand side. So the left-hand side is predicted by the right-hand side or something like that. The formula formulas in R always contain this tilde. So the tilde splits the left-hand side and the right-hand side. We have our data. So when we look at the data, we're gonna work with the prestige. We're gonna work with the subset, or let's do the real data because we might want to use the type. And the dependent variable is income. So we type income, and then we have the independent variables. They're gonna be education plus women plus prestige. And that's going to be enough for now. And this is not sufficient for R because we also have to define which data we apply and apply the regression to. So we do data and prestige. We could also leave out this data and use positional arguments. So the first argument is the formula, and the second argument is the data. But I like to use data here because it's more explicit that this is our data. And then we run that regression, and it just prints something to the console. So this is not super verbose, so we just get the regression coefficients, but we would like to have also the standard errors and the R-scores and that kind of stuff to really interpret the results. So what we do is that we store this regression as M1, and then we do summary. And the reason why I store it is that I want to run diagnostics to this model. I could just do a summary like so. If this was just like a one-off regression and I don't use the results for anything, then I could do that. So this prints the summary, but I like to store the results for diagnostics. So let's take a look at what this output here means, and I'll increase it a bit so it's easier to see. So we have first just the equation, like that's the regression command that we just ran. Then we have some diagnostics on residuals. I don't often use this, but it's useful for kind of like eyeballing if the residuals are normal. The normality of residuals per se is very unimportant for regression analysis, but if the residuals are highly non-normal, that might indicate that there are outliers, or that might indicate that we need a nonlinear model. This residual distribution here doesn't really tell us what the problem is, but we can see that the minimum residual is minus 7,000. The maximum is 14,000. So this means that the worst prediction by the model is off by minus 7,000, so that the occupation that is predicted to have the worst prediction error to the positive direction is 7,000, and the worst prediction error to the negative direction is 14,000. And I know that this is general managers. They make like 25,000 per year, and the model predicts that they make 11,000. So it's off by quite a lot. Then with the regression coefficients, so this is the coefficient, standard error, that's the t-statistic, and that's the p-value. And then we have these regression, these p-values here, and this notation tells that it's 4.19, and this e means this is the exponential or the scientific notation. So this means that there are 8 zeros in front of this p-value here. So this is highly statistically significant. There's 6 zeros here before 7, and that's also highly statistically significant. So from these results, we would interpret that every additional point of women decreases the expected annual income of the occupation by 50 Canadian dollars. And the share of women is coded based on, we can see it here, for example. It's coded between 0 and 100. 0 means no women, 100 means all women, and we could interpret that compared to, if we compare all women and no women occupations, then that is 100 units. So we multiply 100 and minus 50. So all women and all men occupations, all other things being equal, the annual salary difference is 5,000 Canadian dollars, which is quite substantial considering that the most highest earning occupation earned 25,000. Prestige is a strong determinant, so prestige score conceptually varies between 0 and 100, but the actual range is from 15 to 85, so that's 70 units. So from the range of the data, we would multiply 70 times 141, so we can do that in the console. And that will give us that the least prestigious and the most prestigious occupation, the difference is about 10,000 Canadian dollars, assuming share of women and education are equal. Education is non-significant, which is interesting because we would assume that education actually makes a difference for earnings, but it might be that this would actually be a mediation effect, so that education affects prestige and how prestigious occupation you get to, and the occupational prestige determines your salary, not the education. So just getting more education without going to more prestigious occupations might actually not pay off. So that would be the interpretation. Then we have the R square, so it is 64. So we explain the income very well, and this is not surprising because if you think about occupational prestige and education, education is highly correlated with income, and prestige is also highly correlated with income, and in this data, women as well. Adjusted R square is very close to R square, and that means that our model is not overfitting too much. So if the adjusted R square and R square are very different, then that means that you have too many variables compared to your data. And in that case, you should report the adjusted R square, but the adjusted R square instead of the R square. But here, they are so similar that which one we use doesn't really make a difference. And this is the F test for the R square being 0 in the population, and it's strongly rejected, and that's pretty reasonable conclusion because the R square value is actually very high. The next thing that we want to do with the model is to run some diagnostics, and I will start by just showing what you could do, and this comes from my clipboard, so I typed that already in my notes. And if you want to calculate predictions, you can calculate the predictions by using the predict function, and if you want to calculate residuals, you can calculate the residuals with this function. So we can do that. And if we want to study how well the model performs, then we could add these to our data frame, or we can plot them. But there are better ways of doing actual diagnostics. So if you want to understand, for example, if the residuals are normally distributed, we could do plot density residuals R1. And we can see that the residuals are not normal. If we want to plot the residuals versus fitted, we can do fit first and then residual. So we can see that the model predicts these high income occupations much more poorly than these low income occupations, and there's a bit of a negative trend. We would rarely actually work with the residuals and predictive values like this directly, but instead what we can do is do various diagnostic plots that the CAR package provides. And I have this set of diagnostics plots that I often like to do. And QQplot tells you if your residual is normally distributed. So it plots the quantiles of the actual observed residuals and against the theoretical normal distribution. And if the observations are on the line, then it means that they are normally distributed. We can see here also outliers. So we can see that these highly positive residuals are physicians and general managers. The model predicts these observations to be a lot lower paying than what they actually are. So there are positive residuals here. And the useful thing about this plot is that it shows you the outliers. So these are student-test residuals, and it means that they are residuals calculated without the focal observation. So this is the residual of a general managers from a model that doesn't include general managers. Or conceptually it works like that. The math doesn't actually, the regression model is not recalculated. There are ways of calculating what the residual would be without its observation. And why do we do it that way? We do it that way because if we want to understand how different one observation is from others, or how different the observation is from a regression line, then it's better to calculate the regression line without that observation, because every extreme observation kind of pulls the regression line toward itself. So this is like an outlier observation here, and it pulls the regression line toward itself. So the residual is a bit biased because every observation affects the regression line. And if we want to estimate less biased residuals, then studentization is one way of doing it. And you'll see studentized residuals in many diagnostics plots. All right, so, and it also tells us what the observations are. So general managers is observation number 2 and physicians in observation number 24. If we wanted to calculate, show the residuals for these observations, the best way to do it would be to include the residuals in the data. So we could do something like this. So we could do prestige, and let's call it analysis equals mutate. So the mutate is for changing objects. That's tidyverse command, creating variables. We need to define that we mutate the prestige data like so, and now it's in the data set, so we can see that there's 7 variables instead of 6, and we have the R1 here. And if we want to eyeball the data, we can do so here, and we can sort based on the residual, and we can see here what are the low residuals and what are the high residuals from the data. So the physicians is here and the general managers is here. This would be useful if you are interested in particle observations. Generally, in my data analysis workflow, I don't store the residuals in the data frame, but this is something that some researchers do, and particularly if you come from Stata or SPSS, how you would analyze the residuals is that you store it in your data and then it's there. But I just plot them directly. So I will now drop this prestige analysis here. We don't actually need it, so we're gonna delete it from the memory. Just it's a good analysis practice to keep your scope clear, so that you don't have extra stuff. And I will also delete the correlation analysis because I don't need that. All right, then we have these. Let's clean up a bit more. We will keep the prestige subset because I want to be using that later, but let's just keep the data on the model. Getting rid of clutter is a very good idea generally, because if we have, let's say, 5 different copies of the data in the memory, it's very hard to remember at some point which data you're actually working on. All right. So the next thing that we do is all right, let's rather run that again. The next thing that we do is residual versus fitted plot, and the residual versus fitted plot tells us the fitted values, and this is just the normal residuals. And if we want to understand what it does, we can just rerun these plot predictions over residuals, and this is the same thing. So you can see that this is just a fancier way of showing this same plot. So you're plotting a scatter plot where you have the predictions on the X and residuals on the Y, and then we are feeding, we are drawing some nice stuff over here. Importantly, we have the curve here that fits. It's like some kind of polynomial line. This plot tells us that if we look at the reference line, if we had exactly linear relationship, then all the observations would be spread out around this line. But we can see that that's not actually the case. There's some curvilinearity. The curvilinearity can be seen here. On the lower end of fitted values, the residuals are all positive. Here in the middle of the data, the residuals are mostly negative. And here on the high end of the fitted values, the residuals are mostly positive. So we can see that, or they are more positive than negative. And this blue line shows that the curvilinearity. We can also see that we have heteroscedasticity problem. So the observations are a lot more spread out over here than they are over here. And if we were to use this linear model, we would have to use robust standard errors, because this would certainly be a violation of the homoscedasticity assumption that makes a difference. All right, so we have evidence of nonlinearity, and we have evidence of heteroscedasticity, and the QQ plot show that we have outliers, these general managers, and this is physicians. The next thing that we do is added variable plots, and added variable plots basically gives you what is the effect of one variable visually on another, controlling for the others. So this is all the added variable plots. So this is income controlling for other variables except education, and this is education controlling for other variables. And this allows us to first identify outliers, so we can see general management and physicians. This newsboys are a lower end outlier. And also it helps us to detect if there are any non-linearities. We can see that the effect of prestige, there is heteroscedasticity, but it's very difficult to say anything about non-linearity. Same with share of women, there's heteroscedasticity. When there are very little women in the occupation, then it means that there's more variance. So low women occupations can be high income or low income, but when we have a large number of women in the occupation, then it means that it's always low income. These plots are not as clear as the residual versus fitted plot, but they're basically like this. They allow you to inspect linearity and heteroscedasticity one variable at a time. If you really want to understand what these added variable plots do, we can do the added variable plot by hand. And how we would do it is that let's do the education and income, or actually prestige and income might be more interesting. When this happens that there's a plus, it means that there's something missing. So R thinks that there's more input coming to the command, and I miss a parenthesis. So if we compare the added variable plot, this plot here and this plot here, so this is basically the same plot, we just need to draw a regression line here. If we look at just this plot, we can see that maybe there is some non-linearity here, like this might go a bit up here, but it's more difficult to see from here. Residual versus fitted plot. The final diagnostics plot that I like to use is the influence plot, and this comes from the CAR package. And this is outliers. The residual tells you what is the residual, so this is the studentized, excluding the focal observation, and then hat value is something that relates to leverage, and it basically quantifies how far from the mass center of the data the observation is. If you think about a regression line, it would be something like this pen here, then an observation that is in the center here doesn't have much leverage, because if you pull the pen from here, you need a lot of force to make it move. And if the observation is here, like far on the regression line, if you pull the pen here, it moves a lot more easily. So the hat value quantifies basically how much strength the observation has, and the residual explains how strongly it pulls. So if you have an observation with high residual and high leverage or high hat value, then that is an outlier. And then Cook's distance is coded with color. Cook's distance quantifies both of these like leverage and residual at the same time. I don't remember the exact formula, what it does. But what you would do in this plot is that you look at observations that have a high residual and a high leverage, or either of these. So we can see that general managers, physicians, and newsboys are potential outliers. And then we need to think about what to do about this data. And if you see some observations that are very different from others, then there are a couple of things to consider. One is that your model might not be correct. So if we draw the residual plot again, so this shows that the general managers here, physicians is here, and they're also shown in the outlier plot. So you might have outliers because the functional form is incorrect. So the model doesn't explain these data well because this is not the best model for the data. So that is one possibility. The other possibility is that they are observations that don't belong to the sample. If we look at, for example, newsboys, and we want to understand what occupations, what determines the salary of an occupation, then newsboy is a part-time occupation. And we might consider that our analysis should focus only on full-time occupation. So newsboys is like the person who, it's like a mailman who delivers mail. And that's a part-time occupation in the data. And part-time occupations, of course, earn a lot less than full-time occupations. So now we need to make a decision of what we want to do with the data. My recommendation is to focus on the biggest problem first and then fix one problem at a time. And the potential problems that we have is outliers, heteroscedasticity, and nonlinearity. Why do we focus on one problem at a time is that when we fix one problem, then that can also fix other problems at the same time. And if you fix and let's say that we drop a general manager as an outlier here, it might actually be the general manager is not an outlier if we consider a nonlinear model. The second thing is that if you fix one problem, then that can reveal other problems. And if we consider the order of importance, getting the functional form correct is the most important thing to get it correctly. So we're going to do the second regression analysis, and we are going to do the log of income. And we can first check what is the distribution like if we log the income. So if we do just the log of income, so we do plot density, prestige, income, then we can see that it's highly skewed. If we do the plot of, let's copy that just to have it there. If we do the log transformation, then we can see that the distribution is quite different. So now we have a few negative outliers, and then we have this kind of like normal looking shape, a lot more than in the previous plot. So this is like a lot more not normal, and this is closer to normality. The normality doesn't matter per se, but it's useful to understand where the observations are. Now there are two different ways of doing the log, and the way number one would be let's do the is to add a log to the actual dataset. Take a log of income and add it to our dataset. The second one is to specify the log as a part of a model. This is a better alternative, but I'll show the first alternative as well because it's more common. Mutate changes the data, and then we call it ln income equals log income. And the nice thing about these tidyverse functions is that you don't need to specify that this is log of income. If you did this with base R, you would do prestige. You would first copy prestige analysis equals prestige. So we make a copy, and then what we would do is to have adjust this. So we would have prestige analysis $ln income equals log prestige analysis income. So this is a lot more, I think, confusing because you have to define the data here and here compared to using the tidyverse function, which knows that the income, the log of income comes from the same data where the log of income goes, or the income comes from the same data where we put the log. So this is the base data, base R version of the same. We are not gonna use that. We're gonna use the tidyverse approach. So this would create the log, and the log might be useful if you want to, for example, do a correlation table or something like that. And then we can do M2, and then we can do M2B, and the M2B is going to be instead of doing the log of income, we do ln income, and the data are prestige analysis. So this and this give us exactly the same results. So if we do M2 and M2B, we can see that the results are identical. So we can take the log as a part of our model, or we can take the log when we modify our data. And the advantage of this approach is twofold. One, it documents better what is your intention, because the log changes the relationship between the independent variable and the dependent variable. So it means that if we take a log of income or log of the dependent variable, then the effects of the independent variables are going to be relative. So it means that the relationships are exponential instead of linear. So this documents that you are modeling an exponential relationship, and this documents the exponential relationship only if we know what the ln income stands for. I tend to name all my logarithm variables as ln, but if a person doesn't know that, then they wouldn't know what this is about. They wouldn't know that this is actually a nonlinear relationship. The second advantage is that when we start plotting the data, then this model specification stores that it's actually a logarithm, and then the plotting function that we will use is aware of that logarithm, and it can correctly draw the exponential relationship instead of a linear one. And I'll show that I'll keep these both. So I'll keep M2 and M2B in the memory just to demonstrate the difference later. All right, let's do a summary model 2. And if we compare this summary model 2 and model 1, so model 1 is R square 64, model 2 is R square 74. So we can see that there's a substantial improvement, and so it's a better model in terms that it explains the data better. But we are not only interested in the R square, we're interested in understanding, is the model correct for these data? We had the nonlinear effect in this. I will make it a bit smaller so we can see a bit more of the code. We have the nonlinear model effect here. So does this new regression fix this nonlinearity? So that is the more important question than whether it explains the data better. If this model is interpreted, and we should do the diagnostics before we interpret it, but we can see that the effect of women actually here is significant. Education is again non-significant, and prestige is non-significant. And this prestige coefficient of 0.249 means that for every additional point of prestige, income increases by 2.5%. So this means that the effects are not absolute, but they are relative. So previously in the linear model, each additional point of prestige increased the expected income by constant amount, but here it increases 2.5% compared to the current value. So the interpretation of the logarithms is these relative effects. Interpreting this kind of nonlinear effects is a lot easier with plotting instead of reading the coefficients, and I'll do the plotting in a moment. Then we do the same diagnostics for this model. So how I do the diagnostics is that I just copy the diagnostics that I've done before, and just changing the model to be something different. So this is my standard set, and then we run the analysis again. It gives us the plots, and we scroll back just to see what we have. And This is the residuals. We can see that we have two outliers, so babysitters and newsboys, both part-time occupations, and then there's another observation. So we have a negative tail in the residuals. We can view that by plotting the residuals as a density plot. So we can do plot density and then residuals M2. So these are the outliers in the data. So you can see that this is newsboys, babysitters. Then there's another one that is an outlier, and then the others are closer to the actual line. If we go and see the plot, this is the newsboys and babysitters here. That's the third outlier that was not named in the plot, and then this is the rest of the data. But that is not super important. What is more important is the linearity. So we go to the residual versus fitted plot, and we can see here that now there is a lot more linear relationship. There's still some, maybe a little non-linearity, but not as much as before. We have some outliers here that pull this part of the regression line down. So maybe if we take these out, I think these are newsboys and babysitters. If we take these out, then the effect will be closer to linear. There's still some outliers on the positive end. So this is probably general managers here. But other than that, it doesn't look as bad as before. And the error term is pretty homogeneous. Like we have some outliers, but the variance seems to be fairly constant. So everything is between minus 0.5 and plus 0.5, and there's no clear pattern. So that looks good. Then the next thing that we look at is additive ripple plots. We have some potential outliers here, but things look pretty linear. We have maybe a slight heteroscedasticity, but it's just these outliers here. So this might slightly open up like that a bit, but maybe it's nothing to be concerned about. And then we have the influence plot. We can see that babysitters and newsboys are marked as outliers. And now we need to think about what is the biggest problem that we have in the data. And we don't have clear evidence of linearity, of non-linearity. Things look pretty good. Heteroscedasticity looks okay, like there's no severe problems. But I'm a bit concerned that maybe babysitters and newsboys shouldn't be my sample. And when you think about the data, and if you drop something as an outlier, then what you need to do is think if there is a conceptual reason for these observations to not be included in the data. And it's not only about an observation being different empirically, but you need to think about, is there a reason for that observation to be different? And if you think about what kind of occupations babysitters and newsboys are, they're actually part-time in these data. And because they're part-time and most other observations, as far as I know, are full-time occupations, we could say that we are not interested in these part-time observations. We want to focus our analysis to be on just full-time employees. So what we can do is do a third model where we do we drop these outliers and see what happens. So the third model would be without outliers, and how we drop the outliers is that we do filtering. And now the question is that what exactly do we filter? Do we filter in the regression command, or do we filter a dataset? And here's one potential source of confusion and error is that if we filter the observations, so we have prestige analysis here, which is the analysis, the data that we use for analysis. So we do prestige, and we filter based on row names. This basically selects all rows based on row names if the row names are not babysitters or newsboys. So if we run this in the console, it prints us true and false. So it checks if the row names are in this vector. So vector is a sequence of values. If the row names are in newsboys or babysitters, and this negation takes the vector and then inverts it. So or takes the makes positives negatives and negatives positives. So if we have this command here and we run it without the exclamation mark, it finds us rows where the row name is either a newsboy or babysitter, and we can see that there is one of them is here and then another one is here. And if we want to know the row indices, we can do which, and it shows that there are 53 and 63, and we could do prestige analysis, and then just C creates sets, vectors or sets of numbers or sets of texts. So this is going to be 53, 63, and that shows us the data. Yeah, we need to select on rows, not on columns. So that shows us the data. And now the exclamation mark simply, if we do this row names, the exclamation mark simply makes positives negatives and negatives positives. So it's the logical not operator. And we are excluding all observations that are false. So this all excludes the observations. Now the challenge here is that if we run this line now, and then we go back and we run this line, then we will be running this regression analysis with a different set of data than we originally did. And I've seen this problem occur quite a few times. So if you have different versions of the data, it would be a good idea to name them differently so that we don't, if we use something in an analysis, then we no longer filter or modify that dataset in a way that adjusts the analysis. So what we can do here is that we do prestige analysis, no outliers, and we will run it. All right, there's an extra parenthesis in the end. Yeah. Another way of doing this is with a pipe. So the pipe, as I explained before, is a way of kind of like chaining together commands. So we would do prestige analysis, and the pipe command is this. So this is from the tidyverse. There's also a built-in pipe in R, but I prefer the tidyverse version. And the idea here is that we take prestige analysis, and then we feed that into the following command. And we would feed it into the filter. So it becomes the first argument. So this would be saying that we take prestige analysis, then we filter. And we also don't need to have the prestige analysis here, but we can use period. So the period means that whatever data this command is piped with. And this is in a way cleaner and better, because you don't repeat the name of the dataset. And also this is slightly more error prone, because if you happen to have, for example, prestige analysis 2 in the data, it's possible that you take the filtering criterion from one dataset and apply it to another dataset. And this syntax here with the period, which refers to the data that the command receives, is less error prone. So I prefer this approach myself. And we can just have both because they do the same thing. So we're gonna run that, and then I have the documentation here. we drop these because they're part-time occupations. That would be we would need to document that. And then we do the third model, and the third model is the exact same thing as the second model. So we can just copy that model from here, and the only thing that we do differently is that we use the no analysis outliers. And now the row is getting a bit long, so I'm gonna break it from here to keep it readable if I ever work on this on a laptop screen that is smaller. And this is gonna be our model number 3. And then we run it, and we can do an comparison against model 2, and then the R-square is 74, and then M3 it's 78. And of course, if you drop observations that are not well explained by the model, then the explanation of the model goes up, which is pretty natural. So 78%, and this is a very impressive thing. And then we would do the same diagnostics for this model, and I will not run them. I will leave some of this for the students to do. So you need to run this and then interpret the results and see if there are any problems. If there are any problems, then you can consider fixing them. All right. So this is the third model, and what we need to do next is to think about how do we go about interpreting these results. Typically, regression results in a journal article, they are reported as a table. So we need to do a table, and then we need to do figures. These are not normally interpreted or reported in any journal article, but I'm personally a big fan of plotting regression results because they allow you to see how well the model actually explains the data, and also they allow you to interpret the magnitude of the effect. So even if you wouldn't put any plots in your article for space constraints or for other reasons, you should always plot them for yourself to understand what the data look like. And then we're also going to do a correlation table, because you always need to have the correlation table to interpret the regression table. And doing this completes the assignment. And then I will show later how to export this to Word. So exporting to Word is pretty simple once you have done the tables using the right packages. And now we have a few options, and there are maybe half a dozen different R packages for doing tables of model results, and there are at least half a dozen or maybe a dozen of different packages for plotting regression results. We will use the model summary and the marginal effects because they are modern, they are well maintained, they are compatible with a wide range of models, and they also work well with tidyverse functions that we'll be using in this exercise. I'm going to start with regression table because it's the most straightforward thing to do. And the regression table command is model summary. And the model summary, if we take a look at the help of the model summary, it takes models, and the models here is a list of models. So it's either a single model or a list of models. So it shows that it's list, model 1, model 2, model 3, and so on. And if we want to name the models, we can use a named list. And there's lots of examples here, and then there's also examples on the website that supports this package. So we can see model summary. There is these models. It's a list, and then we will just do model summary and list the models and see what it gives. So the regression table is going to be model summary and then list. List is a R data object that can contain various data of various different types. So it doesn't have to be all numbers or all text, but in this and it can be analysis results, and it can be a combination of anything. So it's basically an ordered collection of just about anything. And list can contain other lists. So list is kind of like a very general data type. So we have list M1, M2, M3, So we have 3 regression models, and that gives us a nice regression table. And this is almost something that we could just copy paste and submit to a journal. And of course, there's lots of extra stuff here, and we can take a look at the model, the documentation. For example, in the help, we can see here that there is GOF omit or GOF omit, so we can omit various goodness of fit stuff. So if we don't want to have all this information in the figure in the table, then we can omit some stuff. Another thing that we can do is that, or what I like to do is that I like to have my figure, my analysis results to come to the console instead of the viewer. So we can print that as text, and the option would be Markdown, and also we could do confidence intervals. What I'm going to do here is that I will report the results. I will print them in the console instead of the viewer, and I will do model 3 twice, and I will do variance covariance estimation, which means the different standard errors. So I will do 3 models with normal standard errors, and then the third model with robust standard errors that Stata uses. So you can take a look at the options here. So this is VCOV, and we can see what are the different options. So Stata here is the status heteroskedasticity consistent standard errors. So this will be the robust standard errors that we often see in journals, and there are many others. I would maybe prefer HC3 now, but this is the most common that people actually use because that's what Stata does. Then we don't want to have all this stuff like AIC, BIC, log likelihood, RMSCA. These are typically not interpreted in our field and reported. So we just want to have the R-squared, adjusted R-squared, number of observations, and F. So how would we know what is actually what goodness of fit indices are available? We can do this. There's this get GOF function in the model summary package, and we can just do M1, and that just prints everything that is available. And these are the technical names, and we can see here that the viewer shows them all, so they are not in the same order, but this is basically the statistics that we have here. And we can use these labels to determine what we want, or these names. The R-square, adjusted R-square, number of observations, and F statistic are the ones that we want to have in the table. Then the statistic, we can go to the help, and then the help tells us that what we can do here. Statistic, we want to have confidence intervals instead of standard errors, and then the output is marked down so that it will be drawn into the console, and there we have our regression table. If you want to have it in the viewer instead, you would leave out the markdown, and I like to have these more complex commands to be one option per line, so it's easy to either just comment out things and run it without, or leave some options out. So this would be the regression models, and we could of course customize this table to endlessly. For example, I think there are some decimals, like too many decimals here. We could decrease that in the first model. We could add a table note here explaining what these are. We could adjust these model names, and we could say that this is robust SEs, and that would be a good idea because otherwise it's very difficult to see what is the difference. So we're gonna say this is M list M1, M2, M3, and then this would be M3 robust SE. And I have to have it in quotes because it contains spaces, and then R wouldn't know that it's actually a name. So now we have M3 with robust SEs, and it looks very nice. Okay, so this is the table, and the model summary is basically, it's a very comprehensive. If you take a look at the documentation, there's like tons and tons of options. The defaults are pretty good, but you can customize this endlessly, and it supports a very broad range of different R models. So this is a good package because it allows you to get started very easily, but then it doesn't run, and the defaults are reasonable, and it doesn't run out of options. So if you want to do a very exotic table, you can do it with this package in most of the time without having to actually edit your table in Word or whatever you use for reporting. Okay, then the next thing that we want to do is figures, and the figures that we first want to understand the models, like how do these models differ, and M1 and M3 are the interesting models because we changed the functional form. M2 and M3 are very similar, so I'm gonna plot all of these models, and the command is plot predictions. We need to give the condition, which means that what is the x-axis. So we're gonna, when you plot a model, you plot x-axis. So we plot it, and this shows what is the effect of prestige on income holding other variables constant. And if we want to plot the other variables, then we can do education. This plot has some issues. The first issue is that if you think about the range of the income, particularly this plot is very misleading because it shows that there's a positive effect, so the confidence band is very wide. But it's misleading because it doesn't tell us that the range of income goes to actually 25,000. The second one is that we don't actually know where the data are. So when you plot, there are different ways of actually showing the data. And I talk about these different ways of showing the data in my paper on transformations. So there's lots of example R code in the appendix. But we are going to add points equals 1. And this points adds the actual observations. So this allows us to see how well does the line actually describe the pattern in the data. And we can do this all with points. And now this gives us a better way of looking at the data. So the problem without points is that this is not scaled. Like you see this figure, and it shows that there's an increase, but when you actually add the data, then you see that, okay, because there's so much variation in incomes, this positive trend is actually like something that you wouldn't care about. It's too small. And if we look at this, it doesn't explain these high income occupations well. What we can do now is then plot the same thing, and we're gonna plot model 2, and model 2 is the log transfer dependent variable. And the problem now here is that the data are it doesn't look good. And the reason why it doesn't look good is that this is on a different scale. So this is on an exponential scale, and if we leave out the points, we just plot it, we can see that the log income here is plotted on the original, like this is the exponential scale, and we need to make it actually on the original scale, and we do that by applying a transformation. So we do transform exponential, and you can read about these different transformations in the documentation. So if we go to the plot predictions, then there is a transform, and transform here tells that it is a function that we apply, and we apply the function called exp, which is the exponential function in R. You could apply any other function, but it would be pretty silly to do anything else because we log transformed, and then exponential is the back transform. So what we do is that we run that, and that's a nice exponential plot, and points equals 1. And we can see that it explains the data really well. Well, there is a bit of like, it doesn't really explain this high end, and we could tweak this to be a bit better, but it's good enough. We can do model 3, and maybe it's slightly better because of no outliers. Yeah, it's actually quite a lot different because of these outliers being dropped. All right, so this is the model 3, and now we can compare that. Why did I log transform the dependent variable in the model instead of in the data? So we had here earlier the model 2b, and the model 2b included the ln income, and that will be the income log transform before analysis. So we're going to do the model B, and when we run it, we can see that all the observations are here. So if you want to plot the observations, now the observations actually are log transformed, and the plotting function doesn't understand that it should also exponentiate the observations. So for that reason, it's better to keep the observations as they are, and then apply the log transformation in the model specification instead of applying it to the data. Then you would do all this. You would do both of these to pick the model that you interpret. You can compare, for example, M1 and M2, M3, and then decide that M3 is better, and then you do it for prestige and women, which are significant, and then you interpret what do the results mean. If we start to, for example, interpret this plot here, we could say that low income, the least prestigious occupations, they make about 3,000 according to the model, keeping everything else constant, and then the highest income occupations make about 12,000, holding everything constant. So going from the least prestige, the lowest prestige level to the highest prestige level increases your expected income fourfold. That's a very substantial increase. Okay, then we have the final thing, the correlation table, and the correlation table is something that we need to do, and it's important to do it with the final data. We can do the correlation table by using the model summary. So the model summary has the correlations. We have the data summary correlation. So we would do this for prestige, analysis, no outlier. This is our final data, and that's a correlation matrix. Now, if you think about the correlation matrix in like any published paper, they also have the standard deviation and they have the mean. So how do we get the mean and the standard deviation? We can get them by using this data summary function. So we do data summary, and data summary we do prestige analysis no outlier. And now even though I use this quite often, I sometimes forget how things work, so I need to go back to the documentation. And the data summary here gives us, it tells us the syntax is that we have a formula. So the formula is what comes to the rows and what comes to the columns. And then there's the data. So let's do data equals that, and then we have the formula. We have all variables, so we're going to do all, and then our prestige are no outliers, and then we have the right hand side is the columns. So the columns are mean and standard deviation, and that brings us the mean and standard deviation of the data. Now we have the LN income. We can keep it there if we want. So it doesn't, most researchers wouldn't have it there, but let's keep it there for completeness. And the census code is something that we don't really care about, so we could leave it out. But it doesn't really make a difference. We could filter it out, but yeah, let's not do it here yet. Now the next challenge is that how do we then merge these side by side, because this is a correlation, and then this one is the descriptive statistics, and we need to have them first, have them side by side. And the way we do it by side is that we can see that the data summary, the documentation of the data summary has these add columns. So we can add more columns to the table, and we can add it here, and we just add columns. We add the correlation table, and now that we are adding it, we need to output it as so the output here is data frame. So we need to provide a data set. So it's going to be data, because otherwise it's going to be printing text. So we need to have the data summary correlation to print as data. So we can do it like that. So that's data now. So that's a data set that can be manipulated. And then the data summary prints. That's the correlations. Now we have one problem here that we need to address, and it is that we have the variable labels twice. And what we can do is that instead of doing this, we will do drop the first column. And here I'm using base R because it's just a lot more convenient. This one doesn't have a column name, so it's kind of awkward to refer to. So I'm gonna say that drop the first column. So -1 drops, and I'm gonna drop based on index. I'm gonna drop based on the first column, and that gives us a nice regression table. But now this is a bit still not perfect. There's one tweak that we can do in terms of how the R code looks, and then we can add labels to the data. There's the problem here. One problem is that we repeat this one all the time. So we would like to just say that we are working with one data frame, and then apply these functions always to the same data frame without explicitly naming the data frame. And this also overflows a bit, so I will show another way that we can do. So we can do use pipe. So the pipe is that we're gonna use this data, and then we're gonna apply, take all variables, then this is the and that works. We can still make it a bit nicer by taking the correlation here and then indenting this so that it is everything is kind of like nice and doesn't overflow to the margin. So that is number one. And number two is that we should add labels to the data, like education, income, women. These are the technical names of variables. When we do nice tables, they should have labels instead of technical names of the variables. And we can do the labeling in the R. And to label the data, we need to use a new package which we haven't used before. And the package is called labeled. So we do library labeled, and what we do is that we go to the reporting, and we will just start by adding these labels to the data. So this just adds labels, and then when we label it, we need to rerun the label package, and then we label the data. And then we have the labels available for this, and you can see that it's pretty nice. Now the challenge is that these are still not labeled, and how do we deal with that problem? Well, they are not labeled because the correlation function here doesn't respect the labels, and if we just run the correlation, then we can see that it prints the technical names. We can just change the column names. So we will rename the variables, and they are going to be renamed from 1 to 7 because we have 7 variables in the data. And then you might ask, like, how can I figure this out? Well, I did this on my own, and it's just like you read the documentation and you think about where, like, you run this a little by little. So you run the correlation, you see that it doesn't respect the variable names, and then because it doesn't respect the variable names, and I know that the data summary just takes the column names from whatever the correlation provides, then I know that I have to rename them in the correlation command. So that gives you a very nice regression table. If we want to make it even nicer, we could add a note. And how we add a note is that we do look at the documentation, and the documentation says the notes. Okay, we are going to add a note, and the note is we put it here because it's more about the content. Notes, and it allows us to have multiple notes. We'll just have one, and we're gonna have the n. So we're gonna do paste and then n. So paste joins text together, and then we have n row period. So that's the number of rows in the data, and then there's a missing column, comma. So this gives us a very nice regression table. If we wanted to make it even nicer, we could add the legend for the stars. But if I do these tables, then it's there's like, because you can't really fully format the table in R, like all the borders and that kind of things you have to do in Word. So I might just add the legend for the p-values in Word, because it's just like decoration, it doesn't contain any data. So what I typically format in R is the variable names and all the data. And then if there's like decorative elements, like saying that these are correlations, then I would add the superheading correlations in Word. The ln income is not labeled, so we will label it. We rerun that. Here we have the final table. So that's our correlation table. We can now take a look at the regression table again, because we modeled we added the labels. Then this regression table should be made to respect the labels. So this model summary doesn't respect the variable labels, and it kind of makes sense because the data sets that I have could be different. So this data for M1 and M2 is different from M3 because we dropped outliers, and it's possible that they would have different labels. So we need to rename the coefficients explicitly here in the command, and then there is coef rename option here, and if we search for that, it shows that the coef rename is so this searches the documentation and this searches the current page. So we search for coef rename, and then it can get a named character vector, and then it refers to the variable names that will appear in the table. So this changes what appears in the table, and what we can do is have here, we can have it make these labels, let's say prestige analysis labels. We're going to store this so that we only have to define it once, and we will assign the labels like so. Then we add it here. So I'm going to add it after the before the goodness of fit indices, because logically they come before in the table, so that's a logical order. And it has to be so the problem now here is that this is, if we do class, this is a list, and then it expects to have a vector. So vector is a sequence of commands. We can do onList, and that makes it a vector, and we can do like so, and that will give you a nice table. All right, so this is a bit of like a bonus of how you make it look very nice, but this is something that you should learn because this is important for reproducibility. You want to do minimal processing of your table in Word because that causes errors. Okay, so this is now the final thing, and then I will show how to export to Word after I show how to make a report. And when you're done with any analysis, then it's a good idea to always run everything again and to see that everything works. So that works. We have to fix it. I fixed this before, but I forgot to save. So we're going to run it again just to make sure that everything works. And now that everything works, we are ready to export, make a report out of this. And in RStudio, there are two ways of making a report that I recommend on my course. And in the past, what I've recommended students to do is to do a file and then compile report. And this requires some packages. And then you pick a Word as the output. And this creates your Word file. And then you can edit the report in Word file before you submit, write your interpretations and add headings and that kind of things. So we have the, let's go to the main desktop. Here is the data analysis assignment 1. And what we do first is that we can see that the font size is a bit large because this overflows. So we're gonna decrease the font size a bit, and so that everything fits nicely. And then we have all this output here. What we will do is we will add headings, and we can delete this part. So we could add a heading, and we clear formatting. So this is gonna be the heading 1. We're gonna reassign the style. So this is normal. We reassign to heading 1. And then we type explain what the assignment is about. And then we could add here. So we are gonna do an empty paragraph. We're gonna assign it heading 1. Sorry, the normal, because we're just explaining the analysis. So explain, we will do clear formatting, then we do explain packages, and this output. Yeah, I can just then this is the scheme, and we would explain the scheme results. We would explain results here. And then we would add maybe a heading here. So I'm just gonna add that one there, and this is univariate analysis, and this is how you would start building the report. So the idea is to document the workflow, explain what we did, and explain how you understand the results. All right. So this is the way that I've instructed this in the past, and The downside of this approach is that once you export the Word document, then it's very difficult to change any of this R code. So you would have to copy paste between documents of different versions, and that is generally no idea. But if you like typing in Word, then this would be a way to go. Another way is to use the built-in reporting functions of RStudio. So RStudio includes a system called Quarto, which is for writing reports. And if you work with Quarto, you would start by a new file and a Quarto document. And the Quarto document, we are gonna first make it HTML, because this allows us to preview, and then at the end we'll make it a Word document or PDF that we can submit on the course website. Maybe PDF is a bit better, but if you can't get it to work, then you can go to Word and then submit as a Word. We're gonna call it assignment data analysis 1 and Mikko. Yes, and now this is nice because it has a visual editor, and then it has a source editor. So the idea of visual editor is that this is a bit like what you see is what you get, like Word. So you can actually see what it looks like, and then there are chunks of R code. And then if we go to the source, this shows that this is this kind of dash hashes. This is a level 1 heading. And if you want to have another level of headings, then you would have more hashes. So this would be a level 3 heading. If we want to see what it looks like, we can go to the visual editor, and now you can see that this is a smaller heading. So how you would actually go about doing this is that you would do copy the data and assignment here. So we copy all this R code to the Quarto document, and then this is going to be, I'm just going to delete this all, and I will add a new code block. And how I add a new code block is that it's here. So I'm going to add a new R block, and I will just copy paste all that code here. And if I then want to explain the packages, then I would we could do, for example, so that I will add a code block here, and I would move this here, and then I would add my interpretation here, explain the packages here. We would have the heading would be, you explain the assignment here. Then the data exploration, we probably want to have the part where we do the skim. This would be one part, and we would interpret that block separately. So we would do, that part would go here, and interpretation comes here. If we go to the visual editor, then we could add headings more easily. So this could be introduction, and this would be heading 1, and then this would be then maybe we add the univariate analysis. Maybe this would be maybe the univariate analysis would be another block. So we could add a block. So we can add a block, R block here. So this would be missing data, and then this would be, we would add a heading. So this would be interpretation here, and then they would have heading univariate analysis as a heading, and then we add it as a heading. Now, the question is that how do you then actually see the analysis results and the report that you've written with the interpretations? You do it by clicking on this render. And the render, we're going to have data analysis assignment 1. It's going to be saved as a Quarto document. We're going to render it, and the rendering runs all the R code, and it produces the report, and it comes to the viewer, and we can adjust the in the viewer pane. It's just opened into a new browser, so I'm going to put it on the viewer pane instead, and then you can see it. It runs a small while, and then you can see all the R code, all the output here, all the figures come here, and then your interpretation comes here. So this is a very nice way of writing the report, and then here you would you can publish this. You can then change this to format to PDF, and then it renders as PDF, and then you can, or Word, and then you can submit it to the course website. So this is the second way of producing a report. You can either export the log to Word and write it there, or use this Quarto document and then render as PDF. And the advantage of this approach is that you can actually edit the R code while you interpret the analysis. So we can edit the R code here, and this is kind of like an R analysis and a report all put together in one document. So we can render it as a PDF, and that gives us the PDF, and it goes to the assignment folder. And if you don't have the software installed to render PDFs on the computer, it requires the LaTeX, a LaTeX compiler. Then you can export to Word and then just print to PDF or just submit the Word. If you go to the files, then we can see that it produced the PDF, and the viewer, this is the PDF. If you prefer to view PDFs, then you can also just export this as a PDF, and then it looks very, very nice. But I like HTML a bit more because it's a bit faster to do. Okay, so what other reasons would you want to learn how to do these Quarto documents? The Quarto documents are actually used for real, and many books about R, for example, the R for data science, are written with Quarto. So it's code, explanation, then you can render it as a PDF. Another, maybe we just still write our articles using Word because that's what people are used to instead of writing in Quarto. But I've used this for writing mass customized reports. For example, if you do a survey of companies, then it would be very nice to produce reports to those companies where you analyze each company's response against the other companies in the sample. And this can be used for mass producing reports quite easily. And if I'm making teaching notes, like I want to explain something how you do it in R, then I might do that using Quarto, because that allows me to have the R code and the explanation in the same document, just like a self-contained thing. So this is useful for real work. All right, this concludes the part about the assignment, and then I will continue the screencast by explaining a few more things that you might want to know. And the thing number one is how do you get these tables to Word documents? Because you can run the model summary, the command here, and then let's take the markdown out from there for a while, and then you have this nice regression table. So how do you get this to a Word document? A naive way would be to take a screenshot, and I've actually done that in the past. So I've done tables using LaTeX and then compile to PDF and take a screenshot and put it in my Word document. But these commands actually allow you to export to Word. So we would do output equals table1 docs, and that produces us a Word table, the correlation table, and it wants us to install the pandoc package, so we'll do that. You might need to install the pandoc software on your computer. I'm not sure if this package installs it automatically. So this is table 1, and now we can see the files, and now there is the table 1. We can open it, and let's go to the main desktop. You can see here that this is your table, and you could just export this to copy paste this to Word, and then we could start editing it there, for example, centering these headings and that kind of things. If you want to export the regression table to Word, then what you would do, this is the regression table, table 1, and then this would be table 2, because this is the regressions, and we are gonna run that, and that produces the tables. We can go to the files, and then there's table 2, which is the regressions, table 1, which is the correlation. So let's close it so that we can reopen it. So table 1 is the correlations table, and that's what it looks like. So this is how I do tables in my papers, is exactly like this. It's either state or R, but I export the table in with as much formatting as possible. Each table goes into a separate Word document, and then I copy paste the full document into my article file. The reason for doing it that way instead of just copy pasting the numbers is that when you start copy pasting, or even worse, typing the numbers to Word, then it's possible that there are copy paste errors. So you can see actual published papers where the correlations are off by 1. So for example, you would have something like someone pastes this data for example here, and then everything would be off by 1, and that's very hard to notice in the output. Like in a correlation table, you would notice it because you have the diagonals would be 1s. But if you have a regression table where the coefficients are off by 1, that might be very hard to notice, particularly if your different models contain different variables. Okay, so this is how you get to Word, and I'm just gonna copy paste all that stuff to export to Word, and then I will restore this one to Markdown, and that will be Markdown. And this is the file that I will give to the students. Now, RStudio is the editor that most people use, and it's pretty much installed in most computer labs where I've been teaching. But there's also another editor, and the other editor is called Positron. And the Positron, as I said, is more like, it's a next generation product from the company that makes RStudio. And I will now show Positron, and I will explain why you should consider using this editor instead of RStudio. So I use RStudio for teaching because it's simple compared to Positron, and because it's available. And in 2026, when I'm recording this, Positron is not installed in computer labs, and maybe it just takes time for the IT people to figure out what software people actually need. So how the Positron differs from RStudio, let's increase the font size a bit, is that we have pretty much the same stuff here that we had in R. So we have let's just open the file that we did. So data assignment 1, and we can run it from here, and to just have some data. So the Positron differs in important ways, but let's talk about the similarities first. The similarities are that we have the console here, and then the console here is just the R, and then you have plots here, like you had in RStudio. This is a bit nicer because we have a history of the plots here. There's some some like you can experiment with different labels, different layouts for the figure. If we think that the figure needs to be square in our paper, we can experiment with it. So this is a bit more feature rich than the plot viewer in RStudio. Then we have the data here. Like in RStudio, we can open the data here. So the data explorer is here, and the data explorer is a bit more featured than the RStudio. The RStudio just lists the data, but here we have this nice graphic that shows how the data are distributed, and there's the missingness here. And if we want to look at this in more detail, we can take a look at summary statistics. So it shows us the frequencies, because this is a categorical variable, shows frequencies. This is a continuous variable, it shows us summary statistics. So you can already here explore the data. You can also filter the data. So if we want to filter the data, for example, let's take a look at only those that are greater than, let's say, greater than 12 years, and then we can just look at that data and all these updates. So the data exploration is more featured, and I still recommend that you do the data exploration in R code just to document what you did. But this would be a very useful way of kind of like doing an initial exploration of your data when you have it. And it shows that we have a one filter enabled. Let's close it. Then other differences, we have the session here, like you have in RStudio. So this is the variables, the data that we have in the memory. We would have, it shows other objects if we get them. Then we have connections. So this is database connections if you work in a company. Help is similar to R. So we can just do $LM, for example, and it shows us the help. History is the command history. So I've done quite a lot of stuff in this session already, or it actually persists between sessions, which RStudio doesn't. And then the viewer is the same that you have in RStudio. Now, the differences are that we can have multiple sessions open, and we can have multiple statistical software. This supports Python, and it supports R out of the box. So we can have open here, we can look what we have. So I have a Python here going on. I'm gonna close it because we don't need it, and I have 2 R sessions. So this is like a bit room for confusion that if you have 2 sessions. So we're just gonna close it. And now we will start a new R session, and that we're gonna run this again in R. So then we have the terminal, which allows you to type commands to your operating system. Problems, lists, any problems, like if it notices code that doesn't work. Output contain logs. If you are experimenting with different extensions to Positron, then your developers might want to have things here. And then ports is data connections. Well, I've never used that. And debug is something if you want to develop like an R package, then this would be useful if you want to troubleshoot, but most people will not use that. So you will be using console and problems mostly. And then another difference is that we have the layout is a lot more configurable. So you can configure the layouts here. So these are default. So we can have, for example, notebook just gives you the R, and then what you have here on the side. And then you have the stacked, which is like RStudio. And you can pop this out. So you can, for example, move this to a new window if you want, or you can move it to a panel. So panel would be like here. We can move it to the sidebar. So primary sidebar is on the left, and then we can move it to also to the right. So move it to the secondary sidebar. So the primary sidebar contains these icons here, and so this is your files. So that's your open folder. When you start a project in Positron, you do file and then open folder, and I have already opened the folder, the data analysis assignment 1. So we'll be opening it here. And then when you create a new file, you create a new text file here. You can do new from here, file, and then it asks you what kind of file, and we're gonna do an R file, or we can do a Quarto notebook. We don't need to have new files now. There's a very robust search feature, because this is built on a programmer's editor. The search feature and replace feature is a lot more advanced than what you have in R. Then you have here version control. If you are working with a bigger project, you can have a Git repository, which allows you to do version control so that all changes are tracked. And then if two people edit the same file at the same time, the version control manages conflicts. Then there is debugger. So this is for programmers. And then we have, I don't know, if you want to connect to remote computers, that's possible. And this is the interesting thing and the reason why I use Positron as my main editor. And the reason is that you can install all kinds of extensions here. And I have quite a few extensions that relate to AI here. So I have, for example, Claude extension, I have OpenAI extension, I have Google Gemini extension. And these extensions allow you to use various AI tools. So for example, we would have, we have here, this is the, let's say that this is, let's try Klein. So Klein is one of these extensions, and this is an AI bot or AI coding agent that does R code for you. This is not the one that I use primarily now, but this is just to show an example. So I can tell this agent to do stuff for me. And then I have OpenAI's Codex. You have to pay for this, and I'm not paying for it. So because I have Gemini and Claude subscriptions, we could ask it to do something. So what we can now do is, for example, we could open the data analysis assignment 1, and then we could, for example, now open one of these extensions, and I will open the Claude Code extension, because this is something that I use the most, and it opens as a new tab, and I can ask this AI agent to do coding for me. I could, for example, ask that give me feedback on this educational example. And then it reads the code, it sends it to Claude, and it analyzes it. So you can see that it's reading, and it finds strengths and weaknesses. Redundant code. Same outlier remora twice. And all right, the interesting thing here is that we could basically outsource the full assignment to this AI coding bot. And we could let's do that. So I can just go to the assignment description, and I will have I will just copy paste this, and I will clear my session, and then I will tell it that it needs to implement this data analysis assignment, and I will create a new folder here, and it's gonna be we are gonna call it Claude, and I will tell it to work in Claude. We're gonna let work in Claude folder. Do not look at the other files. And just to make sure that it doesn't see, like now we are looking at this data analysis assignment 1, it knows that we are looking at this file, and I'm just gonna make sure that there is a new file, and let's call it clean slate. We're gonna create an R file, and we're gonna save it. Yeah, then this data analysis as assignment. Write an R file and a Quarto document explaining. R file containing the code and Quarto document that can be submitted as a PDF. And what we do is that we put it in plan mode, and the planning mode first allows the AI to inspect the or think about the problem first, and then it proposes how we would approach the problem, and then we can approve the plan, and then once we have approved the plan, and then it will code it for us. And this is something that I've actually been using in one project. There's one paper that I've wrote that I have not written a single line of R code. I did it fully with Claude and Gemini. I just told what analysis I need, and then the AI wrote it for me. And I'll show you kind of like practical examples of how I would use this in writing the example for this course. So then it asks us questions. So what do we want to have? We want to have a Quarto. It recommends it. And we want to have Quarto and R script file, because I want you to report both the analysis file and the report. And comprehensive exploratory data analysis, yes. And let's do system stepwise. Let's see what it does. And let's see. I'm pretty sure that it will first do a linear model, then it will detect that the effect is actually nonlinear, and then it will plot it, do a log transform dependent variable. So while we are waiting for this tool to process, let me talk about the other tools. So I'm a monthly subscriber to Claude, so I pay, it's like $20, except that I have a yearly subscription, so it's a bit less. So I can use this, and it runs out of quota if you do heavy use, and then you have to wait a couple of hours for your quota to reset. So let's see what it's planning. So it's analysis and report, like I want to have in the assignment. That looks good. It wants to have ggli. I've used that sometimes. And then okay, univariate, bivariate, exactly how I do it. Okay, scatterplot matrix, this is what I do. So the AI is well trained because it does what I would do. Okay, it uses the categorical variable, which I didn't use because I leave it to the second assignment of my course. Then there's the report. Model building, initial model. Okay, that these plots, that I didn't use scale location because I think the residual is fitted as the same. And variance inflation factor, this is bad practice. A lot of people do this, but it's useless. and it doesn't do added variable plots, which I really like for some reason. And then document model, okay. Okay, log linear model. Okay. Let's see what it does. I provide this to as a part of this screencast, so you can see what they are. Yeah, and now there is if you are working with an existing code, it's a good idea to approve what the AI does, and this is for basically 2 or 3 reasons. One is that you don't want to have AI to control a computer, and it's the second one is that if the AI does some changes to your analysis file, you should understand the file yourself. So just kind of like letting it run and going for coffee is not a good idea if you want to ever be able to maintain your analysis file yourself. And the third one is that when the AI does something, it might do it in a different way than what you would do. And when you follow what the AI is doing, then you actually learn things. So I've used this for doing R, and then I've learned quite a few things, like new functions that I didn't know, because the AI has seen a lot more R code and a lot more R packages that I could possibly see during my life. So we're gonna auto accept now, because just to make this fast, and it'll run it, and it'll take a couple of minutes for it to code. So it basically runs the code, reads the results. If there is any need to change the code, then it changes the code, and it kind of like troubleshoots it also for you. It's probably just gonna write it once and then it's gonna be done, because this is a fairly simple thing for the AI to do. So this is one thing that you can do. Then you can also use other AI assistants. There is Positron assistant. So the Positron assistant is a built-in AI assistant, and I have that configured to use Claude. And this requires an API key, which means that you're paying for use. So I pay for 20 euros and I get certain amount of tokens. And when I talk with this agent, then it consumes my tokens. And when I run out, then I have to pay more. So whereas Claude Code is a monthly fee, this will be pay per use. One nice thing about this Positron assistant is that it integrates really, really well to the Positron editor. I saw the integrations after we got the Claude Code completed. Then there is Cline. So the Cline is very similar to Claude Code, but you can use it with any model. And so we can go here and we can click, and I have their provider here, Moonshot AI, which is a Chinese company, and I have their Kimi K2 model. I bought 20 euros worth of tokens from them, and this is it's a very capable coding model, and it's about 1/5 of the price of Claude. And there's quite a lot of different providers that you could use to configure, but I have the Moonshot AI. All these AI bots work the same. If you just want to try out, then maybe getting monthly subscription to Claude for 1 month, and then use Claude Code is the best, because I think the Claude Code is the best coding assistant. Then if you're already using OpenAI, if you're paying for the monthly fee for ChatGPT, then you can use this. But if we ask something, we can say hi, then it tells that I need to upgrade because I'm not paying for OpenAI, and I've logged in, but I don't have an active subscription. Then we can use Gemini. So the Gemini doesn't have a button here, but how we would start Gemini is just type Gemini, and then it runs, and we can ask Gemini what this is about, and it can see here, because we have the data analysis assignment 1. This is our working directory, and we can do IDE to check if its integration is on, and it can see that I have this file open. And we could, for example, say that tell Gemini here ask it to describe what's going on in this data analysis file. Explain this file to me. All right, so now Gemini is running and it's explained. I don't want it to edit anything, so it's just reading what's going on in the project. And now Claude Code wants to run an operating system command, so it's a good idea to read it. So it tells that it wants to go to the folder and then run analysis, and just to see if this works. So this is what Claude Code works. And we are going to allow it to run R script. So we're allowing it to run R in this project. So it's using, no, this is my own. This is not the this is the, I wanted to have the Claude. So it created an analysis file, and then it captures the output, and it created the Quarto document, and it's fixing some problem. So I'm not gonna read it fully here because this is just like a demo project. I don't really care if there are lots of errors, but if this was a real data analysis project, I would be reading this, but I don't want to spend your time looking at me reading what Claude is doing. So it detected a missing data problem, and then it's fixing it. So let's see what it does. ggli, better scatterplot matrix is okay. We could do that, but I think the one that we used is good enough. It's important to pick a package if you want to publish something. So if we wanted to publish something, then scatterplot matrices, then I would probably get something more modern compared to the car, because the car is pretty dated. And so it loads things. It copies the file. Okay, so this is a good idea. You shouldn't edit the data set that you load from a package, because we assume that the data are kind of constant, they don't change. So it omits missing data, exploratory analysis. It does this, I would just do skim. So you can see that there are the bot, because it's very fast at producing code, it tends to produce a lot of code. Then there is some kind of density plots, and it scatter plots, and then a linear fit, correlations, scatterplot matrix. This is with the built-in pairs, I assume, which is pretty weird because it loaded the ggli package. And then we have box plots. So this would be a good for categorical variables. And now it's writing a quick start for how we use this project. And then it does linear model. Okay, looks good. Assumption checking. Then it tells what to look for. And then it's log linear, so it does the same what I do. It does tests, and this is kind of like a matter of preference. I don't like using statistical tests for regression assumptions, because I think it's easier to use the plots, because then you see the problem, and the test tells you if the problem is not zero, and it also detects trivially small problems. So I just make like a judgment call based on what it looks like. And then there is this final model, and there's a lot of code. One thing that these AI bots do is that they like programming. So that's a programming thing, like ifs and fors. I don't use this or I try to avoid using this, because if you just use commands without any of these programming structures, it's more readable for a beginner user. and then there is a summary output. And then we have the Quarto document, and the report is here. And let's ask, it asks us to render it like that. Okay, I will need to post this to the course forum and tell how I will grade it. And then we can render it. So in terminal we can run operating system commands. I'm just gonna quit the Gemini. We don't need that. But we can render, and that will create a PDF for us, and then we can take a look at the report. If you run into problems, we can just copy paste this and copy paste it to Claude Code, and then Claude Code will fix it for us. And then it fixes it. And it asks us to try rendering again. And we are now already in the Claude folder, so we just do a Quarto render report to PDF. If any of the students do the assignment like this, I'm gonna fail you from the course, so you have to do it yourself. But it's just to demonstrate that for real data analysis projects, this would be a useful thing for certain kinds of things. And I'm just gonna copy paste that, and it'll fix it for me. So how do I use these AI coding agents? I would not use it for this kind of project for most of the things. I would rather just like, I would perhaps ask it to do the exploit data analysis, because that's a lot of R code to write. And but I would do the regressions by hand, and then I might do visualizations myself, because visualizations with the CodeBot, because they are actually pretty tedious to do, like labeling the data. Let's do once more, and then I'll show a couple of more AI features using this. And now it created a report for us. So we can open it here, and it's 29 pages long. So I'm not gonna read it, but I will post it to the course forum, so the students can take a look at it and study it in detail. All right, so this is like, you can have it to do analysis for you, and data exploration, really great for that, and then troubleshooting. Now let's go and let's clean. And just to show a clear conversation, and if we have like a specific problem, then this is a useful thing for the specific problem. So let's open the data analysis assignment 1, and I'll just put these to let's split right. So it goes here, and so we organize it a bit, and we don't need to see any of that for now. And let's say that I'm gonna make a copy of this. Because I don't want to mess up the original file. Let's say that I did not have these labels, and I run everything up to that point. I tried to run this again, and there's some weird problem that I can figure it out. And this is another good place to show an AI tool. So sometimes you have a weird problem, and if you click on the traceback, which shows where it happens, there's like something going on in model summary correlation, and I don't know what that is. And I'll decrease the font size a bit so we can actually see a bit more of the output. And this is a feature that I now like to demonstrate. So I have this positron assistant. This is configured, and I'm using Claude to manage configure model providers. The Anthropic is, I have the Anthropic key stored on my computer, and it finds it, and it's using Anthropic's Claude API. And if I have a problem, I can ask it to explain the problem to me. And well, this turned out to be a nice teaching example because my code doesn't work, and what we can do with Claude Code is more powerful than the positron agent. Is that we can say that, tell it to run this code and then fix the error. Run this code and fix the error. So when you have a problem, it might take like easily an hours of troubleshooting in the traditional way, and the traditional way it takes a long time for one particular reason, and it's that these packages that you load, you might not fully know every option there. I'm just gonna completely restart R. So let's do that, and then we run it. Yeah, it works. So the challenge, I don't know what the problem was. So sometimes R behaves in a weird way. So when you troubleshoot some things, you have to know like how the packages work, and you can easily work with like 20 packages in a project. And do you know all the documentation from heart? The answer is no. And the AI is trained with this documentation, so we can we can ask the AI questions. So we can do, for example, here we have the the correlation table, and the correlation table would be here, and I want to have that correlation table, and the correlation table, when I run it, it doesn't have labels. And now we can tell a Claude Code that we move it to plan mode. We tell it that add nice labels to this table, and then it proposes how it would do it. And this is something like I didn't immediately know how to add labels, and I kind of knew that the data summary probably supports some kind of labeling, but I didn't know how it works. So the options are either to read the documentation. I've read it, but not today, so I don't remember it. And I can just ask the AI, like, how would you do it? And it says var label from the label package, and then it writes a plan, and here it makes these labels, and we can just auto accept. Actually, I'm gonna ask before edits. So if we have asked before edits, then it shows that this is the edit that it wants to do, and we can approve it here. So it wants to add these labels, and then this is basically what I did by hand, and it's just automating by AI. So labeling data is something that that I would really use this technique, these tools for. Another thing that we might do is that if we have this, let's say, plot predictions. So we have M3 here, and let's do prestige. And this is a nice plot, but it would be useful to label some of these points. And labeling data, like adding things to the graph, is something that is tedious. So I would like to style this to be journal publication ready. Style this so that it is ready for AMJ journal, ready for label interesting points. So we're gonna add it to do things, ask it to add something. And if you want to learn what it's doing, like why it does something, you can switch it to plan mode, and it's a shift tab. Otherwise, you can just allow it to do it and then approve it. I would, if I am analyzing my existing or improve my existing file, then I always ask the AI to present something which I approve. But if it's just like asking it to export the data, then I run it with auto approve. And now it's running first an R code itself to explore the data. So it can run R code like in the background without writing it into the file, and reads the results, and based on that it writes the file. Yeah, AMJ typically requires clean professional figures. That's okay, but points labeled, it wouldn't do that. And one of the challenges with these AI code editors is that they tend to produce you very verbose code. So it adds stuff. I'm not gonna explain what this all does, but it adds a lot of styling. I would probably do this with at least 1/3 less the code, but it works. And labeling and styling figures is something that is tedious, so I'll have AI do it. And now it's checking that I don't have a package, so it installed the package for me. And now it's trying to update the code again. And it's verifying, and I allow it to run it. And I need to load the package in the beginning, and then it updates the code. So it first like wrote a small thing to test it, and then it fixes the code. And so when you work with this AI agent, it's kind of like working with the agent. It's most of the time it is now it wants to save it, which makes sense because it's gonna be publication quality, and we can see what the plot looks like in a moment. With Gemini or with the OpenAI Codex or with Klein, they all work the same way. I think Claude Code is the best of these tools at the moment, but there is substantial development in these tools, and I'm just gonna it checks that the file exists. Yes, we allow it to do that, and then it writes a summary of what it did. Then we can see, okay, so what does the plot look like? The plot is data assignment 1 dot figure prestige wonder where it put it. Figure prestige, so that would be ANJ style with interesting points labeled. So you can do this kind of like tedious stuff that would require a lot of reading of the documentation of how you actually style a figure, and you can ask it to make it nicer. We could also ask it to make unicorn teeth or whatever, and it'll do that. Okay, so this is Claude Code, and it's useful for doing tedious things like adding labels, working with figures, inspecting errors. Like when your code doesn't run, you can just ask copy paste it to Claude Code and put it in plan mode and tell it to develop a fix. And third, you can do clean slate things, like you can tell it to explore your data. I think this multiplies my research productivity in doing R code by, I don't know how much, 5 times for certain tasks, 10 times for certain tasks, and in certain tasks it's not that useful, but for tedious tasks it's like super useful. All right, let's take a look at then the I mentioned a bit the Positron assistant, which is a built-in AI assistant in the Positron editor, and I have it configured here. And we could, for example, highlight this here, and let's do another one. Let's do rather let's do that one. And we can bring up the positron assistant by Command and I, and we can ask the assistant that how would I improve? How can I improve this table? How could I improve this table? And then it's doing it in line. You can ask questions like, what does this code do? And then it will tell it to you. We could, for example, if we have never used ggplot, we can say that, okay, Command I, we're going to bring it up. This looks very complex. I have not used ggplot. Can you explain why it needs to be so much code? And then it uses Claude to explain the code for you. And then we can ask what are the different elements? What does geom mean in this context? So we can do with code, and then it tells what it means. So you can chat about a specific line, and then we can do new things, like we can do file. We're gonna do a new R file, and it's gonna be R file, and let's save that and close it. And we will do just like an error. So let's just do a sequence of numbers. That produces an error. So this is another thing that Positron Assistant does. And it brings you this fixed and explain. And the explain tells what is the problem, incorrect number of dimensions. You're trying to use 2D index in row column on a 1D vector. Your code, A is a vector with 1 dimension. Syntax, A11 is a 2D indexing used for matrices and frames, which doesn't work on vectors. And then we can ask that explains the problem, and then we can ask it to fix the problem. And fixing gives us the code that would fix it. And here we can either run it, or we can insert it at the console. So we can insert the fixed code here, and this is the correct indexing, and we insert it here, and then we can just take the working code instead. So if you think about like you're just learning R, and you're working with something that is not confidential, which means that, like with my projects, my assignments, I strongly recommend that you configure the Positron Assistant for you, because this is gonna save you a lot of time by having it explain your problems to you. So this is the Positron Assist. Positron, I just kind of skimmed the surface of what is possible, and I focused on the AI tools, but this is really a programmer's editor, and there's a lot to discover, and some things that I've done in RStudio, and I wondered, like, why can't I do this and that? Then I never run into that problem with Positron, because this is like a big ecosystem of things. This has, if you go to the extensions, there's like search extensions in Marketplace. You can go to there's a Marketplace, and there's like thousands of extensions to this. So you can even run Stata within Positron if you want. All right, so this concludes the video. I showed the data analysis assignment, and then how to get to tables, which is fairly simple, and then I demoed the Positron a bit.